Close your eyes now. Feel the ground beneath you. That surface you rest upon is moving, though you cannot sense it, spinning at over 1,000 miles per hour as Earth rotates, orbiting the Sun at 67,000 miles per hour, carried through the Milky Way at 500,000 miles per hour, drifting through the local supercluster at over 1,000,000 miles per hour. Yet here you are, still, quiet, breathing. This is the first paradox of existence. Motion and stillness coexist. You are both traveling through an incomprehensible cosmic dance and resting perfectly in this moment. Both truths hold. Both are real. Tonight, we journey together through the landscapes of space, time, and reality itself. Not as observers peering through telescopes at distant cold phenomena, but as participants in the universe's oldest conversation. We'll trace the threads that connect your heartbeat to the pulse of stars, your thoughts to the quantum foam of space-time, your existence to the fundamental forces that weave reality into being. Let yourself drift. There is nowhere you need to be, nothing you need to do. The universe has been unfolding for nearly 14 billion years. It can wait for you to rest. Look up at the night sky, even in your mind's eye. Those points of light are not showing you the present moment. They are windows into history, each star a time capsule transmitting its ancient light across the void. The nearest star to us, Proxima Centauri, lies just over 4 light years away. When you see its faint red glow, you witness that star as it was 4 years ago. The light left its surface when you were slightly younger, traveled through the emptiness of space at 186,282 miles per second, and only now reaches your eyes. Polaris, the North Star, shines with photons that began their journey 433 years ago. That light was born when Galileo first pointed his telescope toward Jupiter, when Shakespeare walked the earth, when the world knew nothing of electricity or engines, or the very nature of light itself. The Andromeda Galaxy, that soft smudge visible on dark nights, reveals itself as it existed 2.5 million years ago. The light you see tonight left Andromeda when our ancestors were just learning to use stone tools, when the human story was barely beginning to be written. Those photons traveled through empty space for longer than our species has existed in its current form. And the farthest objects we can observe, galaxies near the edge of the observable universe, show us light that has been traveling for over 13 billion years. We see those ancient galaxies as they were when the universe itself was young, when the first stars were just beginning to forge the elements that would one day become planets, oceans, and you. The night sky is not a snapshot of now. It is a layered archive of cosmic history, each point of light arriving from a different era. When you gaze upward, you are looking backward through time, witnessing the universe's autobiography written in starlight. The fabric of space. We think of space as empty, a void, an absence. But this intuition misleads us. Space is not nothing. It is a thing itself, a fabric that can bend, stretch, ripple, and flow. Imagine space-time as an infinite ocean, vast, deep, seemingly still on its surface, yet moving in complex currents beneath. Masses create dips and curves in this ocean, like weights placed on a stretched rubber sheet. The Earth creates a gentle depression. The Sun creates a deeper well. Black holes create whirlpools from which nothing can escape. When you drop an object and watch it fall, you're witnessing something profound. The object isn't being pulled by gravity in the way we once imagined. It's following the natural curve of space-time itself. Like a marble rolling along a curved surface, objects move along the shortest path through the geometry of space. Gravity is not a force reaching out through emptiness. It is the shape of reality itself. This fabric can carry waves, just as water carries ripples. When two massive objects spiral into each other, black holes locked in a final embrace, neutron stars colliding in catastrophic fusion, they shake the fabric of space itself. These gravitational waves spread outward at the speed of light, stretching and compressing space as they pass. We have detected these ripples. Instruments sensitive enough to measure distortions smaller than a proton have felt the echoes of collisions that occurred billions of years ago, billions of light years away. The universe has been whispering its most violent secrets across space-time, and we have finally learned to listen. Space breathes. It expands, carrying galaxies apart like leaves on a flowing stream. It curves around mass, creating the invisible architecture that guides all motion. It vibrates with the echoes of cosmic events. It is dynamic, alive in ways we're only beginning to understand. Between the stars, space seethes with quantum activity. Virtual particles flash into existence and vanish in fractions of a second, borrowing energy from the vacuum itself. The emptiness buzzes with possibility, with potential, with fields that permeate everything. You exist within this fabric. Every breath you take happens in space-time. Every thought travels along neural pathways embedded in this cosmic weave. You are not separate from space. You are a pattern within it, a temporary configuration of matter and energy flowing through the universe's eternal structure. Time. Time feels like a river carrying us forward, second by second, from past to future. But Einstein revealed something stranger. Time is relative. It flows at different rates depending on motion and gravity. On the International Space Station, astronauts age slightly slower than people on Earth. The difference is tiny, mere milliseconds over months, but it's real and measurable. Time itself runs faster in orbit than it does at Earth's surface. When astronauts return home, they have traveled a fraction of a second into Earth's future. Near massive objects, time slows dramatically. If you could hover just outside a black hole's event horizon, time would pass so slowly for you that you could watch the entire future of the universe unfold in what felt like moments. Billions of years would pass in the external universe while you experienced only hours. The river of time would become a crawl, nearly stopping at the edge of the ultimate cosmic abyss. GPS satellites must account for time dilation. They orbit at high speeds and experience weaker gravity than we do on Earth's surface. Without corrections for relativity, the satellites would quickly drift out of sync, and your navigation would become useless. Our everyday technology relies on understanding that time flows differently in orbit than it does on the ground. But time's strangeness goes deeper. The past, present, and future may not be what we think. In relativity, all of space-time exists simultaneously. A four-dimensional block where past and future are as real as the present. The flow of time might be an illusion of consciousness, a way our minds organize and process information as we move through this fixed structure. Imagine space-time as a vast landscape. Every moment that has ever occurred or will occur exists somewhere in this landscape. The past doesn't vanish, it remains, a frozen territory we can no longer access. The future isn't yet to be written, it already exists in the topology of space-time, waiting for your world line to intersect with it. You are not moving through time. You are a four-dimensional structure extended through space-time, from your birth to your death. What you experience as now is just where your consciousness happens to be focused within this larger pattern. The baby you are still exists in the past regions of space-time. The elder you will become already exists in the future regions. All of you, across all moments, forms a single continuous thread woven into the fabric of the universe. This is not philosophy. This is the geometry revealed by Einstein's equations, confirmed by every experiment we've conducted. Time is not separate from space. It is woven together into a unified space-time, and in this union, our intuitive understanding of past, present, and future dissolves into something far more mysterious. Cosmic distances. How do you measure something so vast that human scales become meaningless? How do you comprehend distances so large that even light takes billions of years to cross them? Let's begin with light years. The distance light travels in 1 year. Light moves at 186,282 miles per second. In 1 second, it could circle Earth's equator more than 7 times. In 1 year, it travels nearly 6 trillion miles. The nearest star beyond our Sun is about 4 light-years away. That means it's roughly 24 trillion miles distant. If you could somehow travel at 1,000,000 miles per hour, faster than anything humanity has ever built, the journey to that nearest star would take over 2,700 years. Our Milky Way galaxy spans about 100,000 light-years. The light from stars on the far side of our galaxy, the ancient photons that might be arriving at Earth right now, began their journey 100,000 years ago. They have been traveling through space longer than modern humans have existed. The Andromeda Galaxy, our nearest large galactic neighbor, lies 2.5 million light-years away. The light we see from Andromeda tonight left during the Pliocene epoch, when Homo habilis was just emerging, when the world was warmer and sea levels higher, when the continents were still drifting toward their current configurations. The observable universe extends about 46 billion light-years in any direction. This distance seems impossible. How can we see 46 billion light-years away when the universe is only 13.8 billion years old? The answer lies in expansion. As light has traveled toward us, space itself has been stretching, carrying the source of that light farther away. The most distant light we observe comes from objects that were once much closer, but the expansion of space has carried them to these extreme distances. Beyond this observable horizon lies more universe, perhaps infinitely more. But we cannot see it. Light from those regions hasn't had time to reach us yet. The observable universe is simply the sphere of all the light that has been able to arrive at our location since the beginning. Within these vast distances, structures beyond comprehension exist. Galaxy superclusters spanning hundreds of millions of light-years. Cosmic filaments of galaxies stretched across billions of light-years, forming the largest structures in the universe. Voids of nearly empty space larger than the distances between galaxy clusters. And between all of this, mostly space. Vast, dark, patient space. If you could shrink the sun to the size of a grapefruit, Earth would be a small seed about 50 feet away. The nearest star would be another grapefruit 2,500 miles distant. The universe is mostly emptiness punctuated by rare islands of matter and light. Yet within this emptiness, we exist. Conscious, aware, able to measure and comprehend these distances. Able to look across billions of light-years and understand what we see. The universe has organized itself into patterns complex enough to contemplate their own context. You are the universe measuring itself, knowing itself, wondering at its own vastness, the speed of light. Nothing can travel faster than light through space. This isn't an engineering limitation. It's not that we haven't built powerful enough engines yet. It's a fundamental law of reality itself, woven into the structure of space-time. Light speed is not just fast. It is the speed of causality, the maximum rate at which cause and effect can propagate through the universe. It is the speed at which electromagnetic waves travel, yes, but more fundamentally, it is the conversion factor between space and time in the equations of relativity. When you look at light, you see something that experiences no time. From light's perspective, if such a thing can be said to exist, its journey from source to destination happens instantaneously. A photon emitted by a distant quasar billions of years ago experiences no passage of time during its journey to your eye. It is born and arrives in the same moment from its own reference frame. This creates strange consequences. As objects approach light speed, time slows for them relative to the rest of the universe. Length contracts in their direction of motion. Mass effectively increases, requiring more and more energy to accelerate further. At light speed, these effects would become infinite. Time would stop, length would contract to zero, mass would become infinite. The universe itself forbids crossing this threshold, but there's a loophole. Space itself can expand faster than light. Distant galaxies are receding from us at speeds exceeding light speed, carried by the expansion of space itself. This doesn't violate relativity because nothing is moving through space faster than light. Space itself is growing, carrying galaxies along with it. Light speed also defines horizons in the universe. Beyond certain distances, space expands so rapidly that light can never bridge the gap between there and here. Objects beyond this cosmic event horizon are forever beyond our reach, not because they're far away, but because the expansion of space itself makes them recede faster than light can close the distance. The universe has a speed limit, and it imposes profound constraints. It means we can never know the universe all at once, because information takes time to travel. It means simultaneity is relative. Events that appear simultaneous to one observer occur at different times for another observer in motion. It means the faster you travel, the more you move through time instead of space. Light speed is not arbitrary. It emerges from the deepest mathematics of reality. It is the same in all reference frames, for all observers, regardless of their motion. This simple fact, that light speed is constant, led Einstein to revolutionary conclusions about the nature of space and time themselves. When you see starlight, you witness information that traveled at the maximum possible speed through space-time to reach you. Every photon in that ancient light moved at exactly 186,282 miles per second, never faster, never slower, from the moment it left the stellar surface to the moment it entered your eye. Light is the universe's courier, carrying information at the ultimate speed limit, connecting distant regions of space-time into a comprehensible whole. Dark spaces. The universe is not distributed randomly. Galaxies are not scattered through space like salt thrown across a table. They organize into an immense structure called the cosmic web, a three-dimensional network of filaments and sheets spanning the observable universe. Picture the foam in a glass of water. The bubbles create walls and filaments surrounding empty voids. The cosmic web looks remarkably similar at vast scales. Galaxy clusters and superclusters form the filaments, connected by bridges of galaxies and dark matter. Between them stretch enormous voids, regions of space hundreds of millions of light years across, containing very few galaxies. These structures formed from tiny variations in the density of matter in the early universe. Slightly denser regions attracted more matter through gravity, growing denser still, eventually forming the seeds of galaxies and clusters. Gravity pulled matter into these overdense regions, leaving the voids relatively empty. Over billions of years, this process created the web we observe today. The filaments glow faintly with hot gas falling into galaxy clusters along these cosmic highways. Recently, astronomers detected this glow directly, observing the gas threading through the cosmic web, confirming predictions made decades ago. The web is not empty darkness. It contains warm, diffuse gas and invisible dark matter, forming the scaffolding upon which visible structures grow. Within the voids, space is not completely empty. A few lonely galaxies drift in these cosmic deserts, isolated, surrounded by hundreds of millions of light years of darkness. Imagine existing in a galaxy in the center of a large void. When your civilization looked up, they would see almost no other galaxies. The universe would appear far emptier, far lonelier than it does from our location in the outskirts of a galaxy cluster. The cosmic web represents the largest structure in the universe. Nothing bigger exists. Beyond this scale, the universe appears roughly uniform, with no larger patterns emerging. This uniformity puzzled astronomers initially. Why should the universe look the same in all directions at the largest scales? The answer may lie in cosmic inflation, a brief period in the universe's first fraction of a second, when space expanded exponentially, smoothing out irregularities. The web continues to evolve. Gravity slowly pulls galaxy clusters together along the filaments. The Milky Way is part of a larger structure called the Laniakea supercluster, a gravitationally bound collection of galaxies spanning 520 million light-years. We are flowing through space toward the center of this immense structure, drawn by the accumulated gravity of trillions of stars. But dark energy, the mysterious force accelerating the universe's expansion, will eventually overwhelm this inward pull. In the distant future, the cosmic web will stretch and thin. The voids will grow. Galaxy clusters will become increasingly isolated as space expands between them. Eventually, In hundreds of billions of years, the web will dissolve. Galaxy clusters will become island universes, separated by such vast distances that light from other clusters will never reach them. For now, we exist in an era when the cosmic web is visible, when we can map its structure and trace our position within it. We have discovered that we live in a universe with architecture, with a grand structure emerging from simple laws and the passage of time. The cosmos is not chaos. It is order expressing itself across scales that dwarf human comprehension. Stars. Every atom heavier than hydrogen in your body was forged inside a star. The calcium in your bones, the iron in your blood, the carbon in your DNA. All were created through nuclear fusion in stellar cores billions of years ago, then scattered into space when those stars died. Stars are not just points of light. They are fusion reactors, crushing hydrogen atoms together under immense pressure and temperature, converting mass into energy according to Einstein's famous equation, E=mc². This process releases the light that allows them to shine for millions or billions of years. Our sun converts about 4 million tons of mass into energy every second. This sounds like a staggering amount, but the sun is so massive that it can sustain this reaction for roughly 10 billion years. It is currently middle-aged, about 4.6 billion years into its lifespan. Stars come in many varieties. Red dwarfs, the most common stars in the galaxy, are small and cool, burning their fuel so slowly they could shine for trillions of years, longer than the current age of the universe. Some red dwarfs born early in cosmic history will still be shining when the last massive stars have long since died. Blue giants burn hot and bright, exhausting their fuel in mere millions of years. They live fast and die young, exploding as supernovae and seeding space with heavy elements. Their brilliance can outshine entire galaxies, but their time is brief. In between lie stars like our sun, yellow dwarfs that balance fuel consumption with longevity, providing stable energy for billions of years. This stability may be necessary for complex life to evolve. Planets orbiting more erratic stars might experience too much variation in energy output for life to establish itself. Inside a star's core, hydrogen fuses into helium at temperatures exceeding 15 million degrees. The energy released creates pressure that holds the star up against the inward pull of gravity. This balance, between gravity crushing inward and fusion pushing outward, maintains the star's stability. When hydrogen in the core depletes, the star's fate depends on its mass. Stars like the sun will swell into red giants, burning helium and creating carbon and oxygen. Eventually, they'll shed their outer layers into space, forming beautiful planetary nebulae, leaving behind a dense white dwarf core that will cool slowly over trillions of years. Massive stars undergo more dramatic transformations. They fuse heavier and heavier elements, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each fusion stage releases less energy and proceeds more quickly. A massive star might burn hydrogen for millions of years but consume its silicon in mere days. Iron cannot fuse to release energy. When a massive star's core becomes iron, fusion stops. The outward pressure vanishes. Gravity wins. The core collapses in a fraction of a second, then rebounds in a catastrophic explosion. A supernova. For a brief time, a single exploding star can outshine an entire galaxy. In that explosion, elements heavier than iron form. Gold, platinum, uranium. These elements require conditions even more extreme than stellar cores, conditions that exist only in supernovae and neutron star collisions. The gold in any jewelry you might wear was likely created in a supernova explosion billions of years ago, then incorporated into the cloud of gas and dust that formed our solar system. Some massive stars don't explode. They collapse completely into black holes, objects so dense that space-time curves back on itself, creating a one-way trap for anything that crosses the event horizon. Not even light can escape. Stars older than the universe would appear to exist, but these age estimates have been refined. The oldest stars we've found are about 13.5 billion years old, formed when the universe itself was only a few 100 million years old. They contain almost no heavy elements, just hydrogen and helium from the Big Bang, with trace amounts of lithium. They are witnesses to the universe's youth, fossils from an era when the cosmos was just beginning to illuminate. Between stars lies dust and gas, the interstellar medium. Dense regions of this medium collapse to form new stars. The process continues. Old stars die, enriching space with heavy elements. New stars form from this enriched material. Each stellar generation contains more heavy elements than the last. Our Sun is a third-generation star, born from gas enriched by the deaths of earlier stars. Star formation continues throughout the galaxy, though it has slowed from its peak billions of years ago. We can observe star-forming regions like the Orion Nebula, where new stars are being born right now. In a few million years, that nebula will disperse, and a new star cluster will shine where the nebula exists today. Stars are not eternal, but their legacy is. Every element, every atom, every molecule in your body participated in this cosmic cycle. You are made of stardust, not metaphorically, but literally. The universe created you through billions of years of stellar alchemy, through countless cycles of birth and death in the hearts of stars. Galaxies. The Milky Way, our home galaxy, contains between 200 and 400 billion stars. It stretches about 100,000 light-years across, a vast rotating disk with spiral arms winding outward from a dense central bulge. At the very center lies a supermassive black hole, Sagittarius A, with a mass 4 million times that of the Sun. We exist about 27,000 light-years from this galactic center in a minor spiral arm called the Orion Spur. We orbit the galactic center at about 515,000 miles per hour, taking approximately 230 million years to complete one orbit. The last time we were in this position, dinosaurs were just beginning to diversify. The next time we return to this spot, Earth will be unrecognizably different. From our position within the disk, we see the Milky Way as a band of light across the sky. Ancient cultures told stories about this luminous river. The Greeks called it the Milky Circle. In Chinese astronomy, it was the Silver River. Maori traditions described it as a canoe. Not until Galileo pointed his telescope skyward did we realize this soft glow was composed of countless individual stars, too distant to resolve with the naked eye. Galaxies come in several shapes. Spiral galaxies like the Milky Way and Andromeda display beautiful rotating arms where star formation actively continues. Elliptical galaxies appear as smooth, featureless collections of stars, typically older systems where star formation has ceased. Irregular galaxies lack clear structure, often the result of gravitational interactions or mergers with other galaxies. The Andromeda Galaxy, visible to the naked eye as a faint smudge in dark skies, is approaching the Milky Way at about 70 miles per second. In approximately 4.5 billion years, Andromeda and the Milky Way will collide. This sounds catastrophic, but galactic collisions are strangely gentle. Stars are so far apart that direct collisions between individual stars are extremely rare. Instead, the galaxies will pass through each other like ghosts, their gravitational interactions reshaping both systems. Over billions of years through multiple passes, the two galaxies will merge into a single large elliptical galaxy. Astronomers have named this future galaxy Milkomeda. By the time this merger completes, the Sun will be nearing the end of its life. Earth, if it still exists, will occupy an unrecognizable position in a transformed galactic landscape. Most galaxies contain supermassive black holes at their centers. These black holes can have masses millions or billions of times that of the Sun. They grow by consuming gas, dust, and stars that venture too close. As matter falls into these black holes, it heats up and emits intense radiation, sometimes outshining the entire galaxy. These are active galactic nuclei, among the most luminous objects in the universe. Quasars are the most extreme active galactic nuclei, powered by supermassive black holes consuming matter at prodigious rates. The most distant quasars we observe are more than 13 billion light-years away, showing us galaxies as they were when the universe was young. These ancient quasars tell us that supermassive black holes formed remarkably early in cosmic history, though we still don't fully understand how. Galaxies don't exist in isolation. They cluster together, bound by gravity. Our Milky Way is part of the Local Group, a collection of about 80 galaxies dominated by Andromeda and the Milky Way, with many smaller dwarf galaxies orbiting these larger systems. The Local Group spans about 10 million light-years. The Local Group is part of the Virgo supercluster, which in turn is part of the larger Laniakea supercluster. These structures represent the largest gravitationally bound systems in the universe. Beyond supercluster scales, dark energy dominates, and expansion pulls structures apart faster than gravity can draw them together. Between galaxies lies intergalactic space, vast regions of near-perfect vacuum. Yet even here, gas exists, extremely diffuse, but detectable. This intergalactic medium contains about half of the universe's normal matter, spread so thinly it's nearly invisible, yet present throughout the cosmic web. Some galaxies have been ejected from galaxy clusters at high speeds, now flying through intergalactic space. These rogue galaxies travel through the void for billions of years, gradually using up their gas reserves, their star formation slowly dying. They are cosmic wanderers, cut off from the gravitational dance of clustered galaxies. The universe contains about 2 trillion galaxies in the observable universe, each with millions to trillions of stars. The total number of stars in the observable universe likely exceeds 10^24, more stars than grains of sand on all of Earth's beaches, and each star might have planets, some potentially harboring life. We have photographed only a tiny fraction of these galaxies, yet every deep field image reveals thousands more. Point the Hubble Space Telescope at what appears to be empty space. Let it gather light for days, and thousands of previously unknown galaxies appear. Each one is a vast stellar city, each with its own history, its own structure, perhaps its own civilizations looking back at us across the emptiness. Black holes. Black holes are regions of space-time where gravity becomes so intense that reality itself seems to break down. At their cores lie singularities, points where density becomes infinite, where the known laws of physics cease to make sense. A black hole forms when matter compresses into an impossibly small volume. For a stellar mass black hole, created by the collapse of a massive star, all of the star's remaining mass, perhaps 10 times the mass of the Sun, compresses into a point smaller than an atom. The resulting gravitational field is so strong that within a certain distance, called the event horizon, even light cannot escape. The event horizon is not a physical surface. It's a boundary in space-time, the point of no return. Cross it, and your fate is sealed. You will reach the singularity. There is no escape, no way to reverse course. Time itself points inward, toward the singularity, just as surely as it points forward outside the black hole. Strange effects occur near black holes. Time dilation becomes extreme. If you watch someone fall toward a black hole from a safe distance, you would never see them cross the event horizon. Time would slow for them relative to you, and they would appear to freeze, red-shifting and fading as their light struggled to escape the intense gravity. Meanwhile, from the falling person's perspective, they would cross the horizon in finite time, though they couldn't survive the journey. Tidal forces near black holes are enormous. The difference in gravitational pull between your head and feet would become so great that you'd be stretched like taffy, a process morbidly called spaghettification. For stellar mass black holes, this would happen far outside the event horizon. For supermassive black holes with much larger event horizons, tidal forces at the horizon itself would be weaker. You might cross the event horizon intact, though your doom would still be certain. What happens inside a black hole? We don't know. Einstein's equations predict a singularity at the center, but singularities represent mathematical breakdowns, points where the equations produce infinite values and cease to make physical sense. Most physicists believe that quantum effects, not yet incorporated into our understanding of gravity, prevent true singularities from forming. Black holes are not cosmic vacuum cleaners, despite popular imagery. They don't suck in surrounding matter with supernatural force. Their gravitational pull at a distance is identical to any other object of the same mass. If the Sun suddenly became a black hole, Earth would continue orbiting exactly as before. We would freeze in the darkness, but we wouldn't spiral inward. Black holes can spin, and this rotation drags space-time around with them, an effect called frame dragging. Near a rotating black hole, space itself rotates, and nothing can remain still. The ergosphere, a region outside the event horizon, forces everything within it to rotate with the black hole. Supermassive black holes, millions or billions of times the Sun's mass, lurk in the centers of most galaxies. How they formed remains mysterious. Did they grow gradually by consuming matter? Did they form from the direct collapse of massive gas clouds in the early universe? We're still piecing together this history. In 2019, we captured the first image of a black hole's shadow. The Event Horizon Telescope photographed the supermassive black hole at the center of galaxy M87. The image showed a ring of glowing gas surrounding a dark central region where the black hole's gravity bends light around it. This shadow, larger than our entire solar system, represented a confirmation of decades of theoretical predictions. Hawking radiation suggests that black holes aren't entirely black. Quantum effects near the event horizon should allow black holes to emit faint radiation, slowly evaporating over time. For stellar mass black holes, this process would take longer than the current age of the universe by many orders of magnitude. For the smallest hypothetical black holes, evaporation would be rapid, ending in a final explosive burst. This radiation creates the black hole information paradox. When matter falls into a black hole, what happens to the information about its quantum state? Hawking radiation appears to be purely thermal, carrying no information. Does information truly vanish, violating quantum mechanics' fundamental laws? Or is information somehow encoded in the radiation in ways we don't yet understand? This paradox remains unresolved, pointing to deep tensions between quantum mechanics and general relativity. Black holes might be connected by wormholes, theoretical tunnels through space-time, but wormholes, if they exist, are probably unstable, collapsing too quickly for anything to traverse them. They might require exotic matter with negative mass to hold them open, and we've never observed such matter. At the end of a black hole's life, after unimaginable spans of time, after every star has died and every galaxy has faded, black holes will be among the last remaining structures. They will evaporate slowly through Hawking radiation, eventually vanishing in final bursts of energy. And then even these, the universe's most enduring structures, will be gone. Nebulae. Nebulae are clouds of gas and dust in space, illuminated by starlight or glowing from internal energy. They are among the most beautiful objects in the cosmos, vast tapestries painted with the elements of creation. The Orion Nebula, visible even to the naked eye as a fuzzy patch in Orion's sword, is a stellar nursery. Within this cloud, about 1,300 light-years away, new stars are being born. Dense regions of gas collapse under their own gravity, heating up until nuclear fusion ignites. The nebula glows from the ultraviolet light of young, hot stars, which ionizes the surrounding hydrogen, causing it to emit visible light. Planetary nebulae form when sun-like stars die. As these stars exhaust their fuel, they swell into red giants, then shed their outer layers into space. The exposed hot core, now a white dwarf, illuminates these expanding shells of gas, creating beautiful structures. The Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, each is a star's final artwork, a testament to its life's end. Despite the name, planetary nebulae have nothing to do with planets. Early observers through small telescopes saw their round, disc-like shapes and thought they resembled planets. The name stuck, even after we understood their true nature. Supernova remnants mark where massive stars exploded. The Crab Nebula is perhaps the most famous example, the expanding debris from a supernova observed by Chinese and Arab astronomers in 1054 CE. That explosion was bright enough to be visible during daytime for weeks. Now, almost 1,000 years later, the nebula spans about 11 light-years, still expanding, still glowing from the energy of that ancient blast. At the center of the Crab Nebula lies a pulsar, a rapidly spinning neutron star, the collapsed core of the exploded star. This pulsar rotates 30 times per second, emitting beams of radiation like a cosmic lighthouse. The pulsar's energy powers the nebula's glow, creating intricate filaments and structures throughout the cloud. Dark nebulae don't glow at all. They are cold, dense clouds that block light from stars behind them. The Horsehead Nebula in Orion is a famous example, a dark silhouette visible only because it's backlit by a glowing emission nebula. These dark clouds often harbor stellar nurseries, their dense cores collapsing to form new stars. Within nebulae, the chemistry of space unfolds. Complex molecules form in the dense cold gas: water, alcohol, formaldehyde, and organic compounds. The building blocks of life exist in these clouds, suggesting that life's ingredients are widespread throughout the universe. Some nebulae stretch for hundreds of light years, vast enough to contain countless solar systems within their boundaries. They are the recycling centers of galaxies, where old stars return their enriched material to space, and new stars form from this inheritance. The colors we see in nebula images often come from different elements. Hydrogen glows red, oxygen green and blue, sulfur orange-red. By examining which wavelengths of light a nebula emits, astronomers can determine its composition, temperature, density, and motion. Each nebula is a laboratory revealing the processes of stellar birth and death. In the distant future, our Sun will create its own planetary nebula. About 5 billion years from now, after exhausting its hydrogen fuel, the Sun will swell into a red giant, expanding beyond Earth's orbit. It will shed its outer layers in successive waves, creating expanding shells of glowing gas. These shells will drift outward, illuminated by the Sun's exposed core, a hot white dwarf about the size of Earth, but containing most of the Sun's original mass. This future nebula will glow for tens of thousands of years before fading, its gas dispersing into the interstellar medium. The atoms that once comprised the Sun will mix with the galaxy's gas, potentially becoming part of new stars, new planets, perhaps even new life forms billions of years hence. The Sun's death will be its final contribution to the cosmic cycle. Emission nebulae glow because their gas is energized. Radiation from nearby hot stars strips electrons from atoms. When these electrons recombine with atoms, they emit light at specific wavelengths. Each element emits its characteristic colors, creating the nebula's distinctive hues. Reflection. Nebulae don't glow on their own. They simply reflect light from nearby stars, appearing blue because dust particles scatter blue light more effectively than red, the same effect that makes Earth's sky blue. These nebulae often surround young star clusters, the remaining dust from the cloud that birthed the stars. The Eagle Nebula contains the famous Pillars of Creation, photographed by the Hubble Space Telescope in 1995, and again with better resolution in 2014. These towering columns of gas and dust, each several light years tall, are stellar nurseries being sculpted by intense ultraviolet radiation from nearby massive stars. At the tips of the pillars, dense knots of gas called eggs, evaporating gaseous globules, are in the process of forming new stars. The pillars probably no longer exist in their photographed form. A supernova explosion may have destroyed them about 6,000 years ago, but the Eagle Nebula lies 7,000 light-years away. The light from this destruction hasn't reached us yet. For now, we see the pillars as they were millennia ago, preserved in the light that has been traveling toward us across the galaxy. Some nebulae are unimaginably vast. The Tarantula Nebula in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, spans about 1,800 light-years. If it were located at the distance of the Orion Nebula, it would span 60 degrees of the sky, 120 times the apparent diameter of the full moon. It would cast shadows on Earth at night. Within nebulae, dust grains play crucial roles. These microscopic particles, often containing silicates, carbon, and ice, provide surfaces where molecules can form. In the cold depths of molecular clouds, hydrogen atoms meet on dust grain surfaces, and combine to form molecular hydrogen. Complex organic molecules build up layer by layer. These dust grains, along with the molecules they help create, will eventually be incorporated into new planetary systems. When you look at images of nebulae, you're seeing not just beautiful cosmic art, but the fundamental processes that make galaxies, stars, and ultimately life possible. You're seeing creation and destruction, death and birth, the eternal cycle that has continued for billions of years and will continue for billions more. Planets. For most of human history, we knew of only 6 planets: Mercury, Venus, Earth, Mars, Jupiter, and Saturn, the worlds visible to the naked eye. Then telescopes revealed Uranus and Neptune. For a while, we thought our solar system's 8 major planets might be unique, a special arrangement unlikely to be duplicated elsewhere. We were spectacularly wrong. In 1992, astronomers discovered the first planets orbiting another star. Not around a sun-like star, but around a pulsar, the rapidly spinning remnant of a supernova. These pulsar planets were unexpected, strange worlds that somehow survived or formed after their star's explosive death. In 1995 came the first confirmed planet around a sun-like star, 51 Pegasi b, a gas giant orbiting its star far closer than Mercury orbits our Sun. This hot Jupiter completed its orbit in just 4 days. It challenged our understanding of how planetary systems form and evolve. Since then, we've discovered thousands of exoplanets, planets orbiting other stars. The Kepler Space Telescope alone confirmed over 2,600 planets by monitoring tiny dips in starlight as planets transit across their stars' faces. Current estimates suggest the Milky Way contains at least 100 billion planets, possibly several times more. Planets are not rare. They're the rule, not the exception. These worlds display astonishing diversity. We've found planets orbiting binary star systems where 2 suns would appear in the sky. We've found rogue planets drifting through interstellar space, ejected from their home systems. We've found planets made primarily of diamond, worlds of molten rock, ice giants larger than Jupiter, and super-Earths, rocky planets more massive than Earth, but smaller than Neptune. Some planets orbit their stars so closely that their surfaces are molten rock, with one side permanently facing the star in tidally locked rotation. Others orbit so far out that their years last centuries, their surfaces frozen in eternal darkness, except for the faint light of distant stars. Hot Jupiters, gas giants orbiting very close to their stars, probably didn't form there. They likely formed farther out and migrated inward, their orbits decaying due to interactions with the protoplanetary disk or through gravitational interactions with other planets. This migration would have disrupted any inner rocky planets, likely destroying them or flinging them into space. We've discovered planets in the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Proxima Centauri b, orbiting the nearest star to our Sun, lies in this zone. TRAPPIST-1, a small red dwarf star, hosts 7 Earth-sized planets, 3 in the habitable zone. These worlds orbit their stars so closely that standing on one planet, you could clearly see the neighboring planets as disks in the sky. Larger than our moon appears from Earth. But habitable zone doesn't mean habitable. Venus sits near the inner edge of our Sun's habitable zone, yet its surface temperature exceeds 800 degrees Fahrenheit due to a runaway greenhouse effect. Mars, near the outer edge, is frozen and dry. Location in the habitable zone is necessary, but not sufficient for life as we know it. Some moons might be more promising than planets. Europa, orbiting Jupiter, has a global ocean beneath its icy shell, kept liquid by tidal heating from Jupiter's gravity. Enceladus, a small moon of Saturn, has geysers shooting water into space from a subsurface ocean. Both moons might harbor life in their dark, deep oceans. Life that exists without sunlight, perhaps thriving around hydrothermal vents, as it does in Earth's deep oceans. Titan, Saturn's largest moon, has lakes and rivers, not of water, but of liquid methane and ethane. It has weather, seasons, and a thick atmosphere. It's the only world besides Earth where we've confirmed stable bodies of surface liquid. Some scientists speculate about exotic life forms that might exist in Titan's hydrocarbon lakes, using entirely different chemistry than Earth life. The diversity of planets challenges our assumptions. We once imagined solar systems would resemble our own. Rocky planets close in, gas giants farther out, orderly and well-spaced. Instead, we find chaotic variety. We find systems where giant planets orbit closer than Mercury. We find systems with all planets roughly the same size. We find systems that seem impossibly unstable yet persist. Many planetary systems are younger than ours. We can study them to understand our own system's history. Other systems are older, having formed when the universe contained fewer heavy elements. These ancient systems challenge our ideas about planet formation. Can rocky planets form in gas clouds with almost no metals or silicates? In our solar system, the story of planets is one of violence and chance. Earth likely formed from countless collisions between smaller bodies in the early solar system. The Moon probably formed when a Mars-sized object slammed into proto-Earth, ejecting material that coalesced into our natural satellite. Jupiter's gravity prevented a planet from forming in the asteroid belt, leaving only rocky debris. Neptune and Uranus may have swapped positions early in the solar system's history. Mars once had liquid water on its surface, rivers carving channels, perhaps lakes or seas in low-lying regions. Its atmosphere was thicker, its climate warmer. But being smaller than Earth, Mars cooled faster. Its magnetic field died. Without this protective field, solar wind stripped away much of its atmosphere. The water vanished. Some escaped to space, some locked into polar ice caps, some trapped underground. Mars became the cold, dry desert we see today. Venus may have had oceans once. Early in the solar system's history, when the young sun was dimmer, Venus might have been habitable. But as the sun brightened, Venus's temperature rose. Water evaporated. Water vapor is a greenhouse gas. The temperature rose further, evaporating more water, creating a runaway process that boiled the oceans away. Ultraviolet light broke down water molecules, and hydrogen escaped to space. Only the oxygen remained, combining with rocks. Venus became a hell world of crushing pressure and searing heat. Earth survived because we orbit in the Goldilocks zone. Not too hot, not too cold. We have a large moon that stabilizes our axial tilt, giving us stable seasons. We have plate tectonics that recycle carbon, helping regulate our climate over geological timescales. We have Jupiter acting as a cosmic vacuum cleaner, its gravity attracting comets and asteroids that might otherwise hit Earth more frequently. We are lucky, the beneficiaries of countless favorable circumstances. Yet with trillions of planets in the galaxy, lucky circumstances will occur billions of times. Even if only a tiny fraction of planets develop conditions suitable for life, the sheer numbers suggest we are not alone. The question is not whether life exists elsewhere, but whether we can ever detect it, communicate with it, meet it. The smallest scales, everything you've considered so far, stars, galaxies, planets, space itself, ultimately reduces to the quantum realm, a domain where reality becomes probabilistic, strange, and deeply counterintuitive. At quantum scales, matter behaves simultaneously as particles and waves. An electron is not a tiny ball orbiting an atom like a planet orbits a star. It's a wave function, a cloud of probability describing where the electron might be found if you measure it. Before measurement, the electron exists in a superposition of all possible locations simultaneously. This isn't philosophical speculation. It's been confirmed by countless experiments. In the famous double-slit experiment, individual particles fired one at a time at two narrow slits create an interference pattern on a detector screen, a pattern that only waves produce. Each particle somehow knows about both slits, interfering with itself, behaving as a wave. But when you observe which slit the particle goes through, the interference pattern disappears. The act of measurement forces the particle to choose one path, collapsing its wave function. This measurement problem sits at the heart of quantum mechanics. Before observation, quantum systems exist in superposition, multiple states simultaneously. Measurement causes the system to collapse into one definite state. But what counts as measurement? Does it require a conscious observer? Does the universe split into multiple branches, one for each possible outcome? Does the collapse happen gradually through interaction with the environment? These questions remain philosophically and scientifically contentious. Particles at the quantum level display discrete quantized properties. Electrons in atoms can only occupy specific energy levels, like standing on steps rather than a ramp. When electrons jump between levels, they emit or absorb photons of specific energies, creating the characteristic spectral lines that allow us to determine the composition of distant stars. Nothing at the quantum level is truly still. The Heisenberg uncertainty principle states that you cannot simultaneously know both a particle's position and momentum with perfect precision. The more accurately you measure one, the less accurately you can know the other. This isn't a limitation of measurement technology. It's a fundamental feature of reality. Particles don't have precise positions and momenta simultaneously. These properties only become definite when measured. This uncertainty means that even in the vacuum of space, at the coldest possible temperature, energy fluctuates. Virtual particle-antiparticle pairs pop into existence, exist for infinitesimally brief moments, and annihilate. The vacuum seethes with this activity, an endless quantum foam of possibility. Quantum tunneling allows particles to pass through barriers they shouldn't be able to cross. An electron facing an energy barrier has a small probability of appearing on the other side, even though it doesn't have enough energy to go over it. This probabilistic process powers nuclear fusion in the Sun. Protons tunnel through the electromagnetic repulsion barrier to fuse. Without quantum tunneling, the Sun wouldn't shine. Atoms themselves are mostly empty space. If an atom was scaled to the size of a football stadium, its nucleus would be smaller than a pea at the center, and its electrons would be tiny waves of probability washing through the entire structure. Matter feels solid only because electromagnetic forces between atoms resist compression, and quantum mechanical rules prevent electrons from occupying the same states. The Standard Model of particle physics describes all known fundamental particles and 3 of the 4 fundamental forces. It includes quarks, which combine to form protons and neutrons, leptons, including electrons and neutrinos, and force-carrying bosons like photons, gluons, and W and Z bosons. The Higgs boson, discovered in 2012, explains how other particles acquire mass through their interaction with the Higgs field permeating space. Yet the Standard Model is incomplete. It doesn't include gravity. It doesn't explain dark matter or dark energy. It contains constants that seem finely tuned for no apparent reason. It suggests that matter and antimatter should have been created equally in the Big Bang, yet the universe contains far more matter. We don't fully understand why. String theory proposes that fundamental particles aren't points, but tiny, vibrating strings. Different vibration patterns correspond to different particles. String theory requires extra dimensions beyond the 3 spatial dimensions we experience. Perhaps 6 or 7 additional dimensions, curled up so small we cannot detect them. String theory promises to unify quantum mechanics and gravity, but it remains unproven, perhaps unprovable with current technology. Loop quantum gravity offers an alternative approach, suggesting that space itself is quantized at the smallest scales, composed of discrete loops rather than continuous fabric. At the Planck length, about 10 mon 35 meters, space-time may have a granular structure, like pixels forming a screen. Below this scale, our notions of distance and time may break down entirely. The quantum realm challenges our deepest intuitions about reality. It suggests the universe is fundamentally probabilistic, not deterministic. It blurs the line between observer and observed. It reveals that emptiness is never truly empty, that measurement creates reality as much as revealing it, that the microworld operates by rules utterly foreign to our everyday experience. Yet from these strange quantum foundations emerges the classical world we inhabit. Somehow, the probabilistic becomes definite. The wave-like becomes particle-like. The quantum becomes classical. This emergence, this transition from quantum to classical behavior, represents one of physics' deepest questions: entanglement. Einstein called it spooky action at a distance and deeply distrusted it. Yet quantum entanglement is real, confirmed by decades of experiments, and forms the basis for emerging quantum technologies. When two particles become entangled, their quantum states become linked. Measure one particle's spin or polarization, and you instantly know the other particle's corresponding property, regardless of the distance separating them. Change one, and you instantaneously affect the other, even if they're on opposite sides of the galaxy. This doesn't violate relativity's prohibition on faster-than-light communication. You can't use entanglement to send information because the measurement results appear random. Only by comparing results with the other observer do you see the correlation. The comparison must travel at light speed or slower. Einstein, Podolsky, and Rosen proposed a thought experiment in 1935 suggesting that quantum mechanics must be incomplete. If entangled particles show perfect correlations when measured, they argued, those properties must have existed all along as hidden variables, predetermined before measurement. Quantum mechanics was just ignorant of these hidden values. In 1964, physicist John Bell showed that hidden variable theories and quantum mechanics make different predictions about the correlations between entangled particles. Experiments overwhelmingly support quantum mechanics. The correlations are stronger than any hidden variable theory allows. The particles genuinely don't have definite properties until measured. Entanglement is real, not a trick of incomplete knowledge. Two entangled photons can be separated by kilometers. Measure one photon's polarization, and the other photon's polarization becomes definite at the same instant, despite the distance. This isn't information traveling between them. It's as if the two photons are aspects of a single quantum system that transcends spatial separation. Entanglement opens possibilities for quantum computing, where quantum bits, qubits, exist in superposition of 0 and 1 simultaneously. Entangle many qubits, and they can represent vast numbers of states at once, enabling certain calculations that would take classical computers longer than the age of the universe to complete. Quantum teleportation uses entanglement to transfer a quantum state from one particle to another without the particles themselves traveling. The original state is destroyed in the process. You can't copy quantum information due to the no-cloning theorem, but the state reappears elsewhere. This isn't Star Trek teleportation. Only quantum information moves, not matter. Quantum cryptography exploits entanglement to create theoretically unbreakable codes. Any attempt to intercept or measure the entangled particles used to transmit a key disturbs their quantum states, revealing the eavesdropping. Several banks and government agencies already use quantum cryptography for secure communications. The philosophical implications disturb many. Entanglement suggests that the universe is fundamentally non-local. Distant regions aren't as separate as they appear. Some interpretations of quantum mechanics suggest entanglement reflects deeper connections, perhaps hints that space itself is emergent, built from entanglement at the most fundamental level. The many worlds interpretation offers one explanation. When you measure an entangled particle, the universe splits. In one branch, you measure spin up and the distant particle is spin down. In another branch, you measure spin down and the distant particle is spin up. The correlation is perfect in each branch, with no spooky action needed. The cost is accepting that countless parallel universes exist, one for each quantum outcome. Entanglement might have played a role in the universe's earliest moments. During inflation, regions of space that are now separated by billions of light years were once close enough to become entangled. This entanglement might explain why the cosmic microwave background shows such uniform temperature. Distant regions know about each other through ancient quantum correlations. Living systems might exploit entanglement. Some research suggests birds use quantum entanglement in their eyes to detect Earth's magnetic field for navigation. Photosynthesis may involve quantum effects that allow plants to transfer energy with remarkable efficiency. The boundary between the quantum and classical worlds might be less sharp than we imagine, with quantum effects present even in warm, wet biological systems. Entanglement reveals that reality isn't made of independent pieces interacting locally. It's a unified whole, where distant parts remain connected through invisible quantum threads. The universe is more interconnected than our everyday experience suggests, bound together by correlations that transcend space itself. Wave function, collapse. Why does measurement seem to collapse the wave function? Why does observing a quantum system force it from superposition into a definite state? This question has haunted quantum mechanics since its inception. Before measurement, a particle's wave function describes probabilities for different positions, momenta, or spins. The particle doesn't occupy one location. It exists as a smear of probability across many locations. But measure the particle, and you find it in one specific place. The wave function collapses from many possibilities to one actuality. What counts as measurement? Does it require consciousness? If a detector measures a particle but no human reads the detector, has measurement occurred? These questions divide physicists and philosophers. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg, says the wave function is merely a mathematical tool representing our knowledge. Measurement doesn't reveal a pre-existing property. It creates a definite property where before only probability existed. Reality is fundamentally observer-dependent. The many-worlds interpretation, proposed by Hugh Everett in 1957, eliminates collapse entirely. The wave function never collapses. It just evolves according to deterministic equations. When you measure a particle, the universe splits. In one branch, you observe spin-up. In another, spin-down. Both outcomes occur, each in its own parallel universe. There's no collapse, no special role for measurement, just endless branching into parallel worlds. This interpretation feels extravagant, creating vast numbers of parallel universes to avoid collapse. Yet it takes the mathematics of quantum mechanics seriously, with no special rules for measurement. Many physicists find it philosophically appealing, despite its seemingly profligate multiplication of realities. Decoherence offers a middle path. When a quantum system interacts with its environment, the environment entangles with the system, effectively measuring it constantly. This interaction causes the different branches of the wave function to become separated, unable to interfere with each other. From our perspective within one branch, the wave function appears to have collapsed. Reality becomes effectively classical through environmental interaction, not through consciousness or measurement. Decoherence explains why we don't see quantum superposition in everyday life. Large objects constantly interact with air molecules, light, cosmic radiation. Environmental factors that decohere their wave functions almost instantly. Only carefully isolated systems at very cold temperatures can maintain quantum coherence long enough to study. Yet decoherence doesn't solve the measurement problem entirely. It explains why we observe definite outcomes, but not why we experience one particular outcome rather than another. In the many worlds view, we experience all outcomes in different branches. In interpretations with genuine collapse, something must select which outcome occurs. Objective collapse theories propose that wave functions collapse spontaneously, without requiring measurement or observation. Large objects with many particles collapse more frequently, naturally creating the classical world we observe. These theories modify quantum mechanics slightly, adding stochastic collapse terms to the equations. Experiments are searching for evidence of objective collapse, but so far quantum mechanics stands unmodified. The measurement problem connects to consciousness in provocative ways. Some interpretations suggest consciousness causes collapse. Only conscious observation creates definite reality from quantum possibilities. This view implies consciousness plays a fundamental role in physics, a position most physicists reject as unnecessary mysticism. Yet the hard problem of consciousness, explaining how subjective experience arises from physical processes, remains unsolved. and quantum mechanics does seem to require an observer-dependent reality. Perhaps consciousness and quantum mechanics are connected in ways we don't yet understand, or perhaps the question itself is misframed. Maybe there's no collapse, no selection of outcomes, just different branches of reality evolving in parallel. Maybe reality is far stranger than any interpretation suggests, requiring entirely new concepts we haven't yet imagined. The wave function collapse problem exemplifies quantum mechanics' profound weirdness. Nearly a century after its development, we still don't agree on what the theory means, even though its predictions are spectacularly accurate. We can calculate, but we cannot fully explain. We can predict, but we cannot fully understand. The quantum realm resists our attempts to grasp its ultimate nature. The true nature of matter. You think of matter as composed of particles, electrons, quarks, protons. But quantum field theory suggests a deeper truth. Particles are not fundamental. Fields are fundamental. Particles are merely excitations in these fields, ripples in a more fundamental substrate. Imagine the universe filled with invisible fields, one for each type of particle. An electron field permeates all of space. When this field is excited in a localized way, we observe an electron. The electron is not a thing separate from the field. It is the field vibrating in a particular pattern. Similarly, there's a photon field, a quark field, neutrino fields, and so on. These fields exist everywhere, at every point in space, at every moment. Usually they're in their lowest energy state, their ground state, and we perceive empty space. But excite these fields, add energy, and particles emerge. This perspective resolves some quantum mysteries. When a particle and antiparticle annihilate, the field's excitation pattern shifts, transferring energy to other fields. Energy is conserved, but the localized excitations we call particles disappear. When particles are created, energy pumps into fields, creating new excitation patterns. The electromagnetic field is the most familiar. Light is a ripple in this field, an oscillating disturbance traveling at light speed. Radio waves, visible light, X-rays, gamma rays. All are electromagnetic field vibrations at different frequencies. The field itself is more fundamental than the photons. Photons are how we perceive the field's quantum behavior. The Higgs field is special. Unlike other fields, its ground state, its lowest energy configuration, is not zero. The Higgs field has a non-zero value throughout space. Particles acquire mass by interacting with this background Higgs field. The more strongly a particle interacts with the Higgs field, the more massive it is. Massless particles like photons don't interact with the Higgs field at all. When CERN's Large Hadron Collider discovered the Higgs boson in 2012, it wasn't finding a new particle in the conventional sense. It was exciting the Higgs field enough to create a localized disturbance, the Higgs boson, which quickly decayed into other particles. The discovery confirmed the Higgs field's existence. Virtual particles emerge from field fluctuations. The electromagnetic field constantly fluctuates at quantum scales, creating virtual photons that exist briefly before vanishing. These virtual particles aren't hypothetical. They have measurable effects. The Casimir effect, where two metal plates in a vacuum attract each other, occurs because virtual photons exist between the plates in different configurations than outside them. Quantum field theory allows for particle creation and destruction, unlike earlier quantum mechanics that tracked fixed numbers of particles. In high-energy collisions, particles transform into different particles. Quarks might become electrons and neutrinos. Protons might produce mesons. The number and types of particles change, but the underlying fields persist. This field-based view suggests that what we call empty space is actually a plenum, a fullness of fields in their ground states. Excite these fields, and matter appears. Let them settle, and matter vanishes. Creation and destruction occur constantly as fields fluctuate and interact. Some physicists speculate that space-time itself might emerge from more fundamental quantum fields. Perhaps space and time aren't fundamental, but arise from the behavior of underlying quantum information or entanglement patterns. This is speculative, bordering on philosophy, but it suggests that even space-time, the stage on which physics occurs, might be emergent rather than fundamental. If fields are fundamental, then you are not made of particles. You are a complex pattern of field excitations, a temporary configuration that maintains itself through constant interaction and energy exchange. The atoms in your body are not things, but processes, patterns of field excitation that persist for a time before the energy flows elsewhere, taking different forms. This isn't metaphor. This is the most accurate description physics offers for the ultimate nature of matter. You are made of fields, vibrating in patterns complex enough to think, to feel, to wonder at the universe that spawned you. You are the quantum fields becoming aware of themselves. Why time has a direction. Time seems to flow inexorably forward. We remember the past, not the future. We age, but never grow younger. Broken glasses don't spontaneously reassemble. Yet the fundamental laws of physics are mostly time-symmetric. They work equally well backward or forward in time. If you filmed billiard balls colliding and played the video backward, the reversed motion would still obey physics laws. The same applies to planets orbiting stars, to electromagnetic waves propagating, even to most quantum processes. The equations don't distinguish past from future. Yet we experience a profound arrow of time, a clear distinction between past and future. Where does this directionality come from? The answer lies in entropy, a measure of disorder or randomness in a system. The second law of thermodynamics states that entropy tends to increase over time. This is not an absolute law like conservation of energy, but a statistical tendency. Systems naturally evolve toward more probable, higher entropy states. A broken glass has higher entropy than an intact one. The arrangement of glass shards scattered on the floor represents more possible configurations than the ordered structure of an intact glass. It's not that reassembly violates physics. It's just extraordinarily improbable. The shards would need to move in exactly coordinated ways, a configuration so unlikely that it effectively never occurs. This statistical arrow of time emerges from the universe's initial conditions. The Big Bang created a universe in a remarkably low entropy state. Everything was compressed, uniform, simple. As the universe expanded, gravity pulled matter into clumps, stars formed, galaxies emerged. Entropy increased as simple uniformity gave way to complex structure. This seems paradoxical. Structure feels more ordered than simplicity. But gravitationally bound systems have negative specific heat. As they release energy, they become more tightly bound and hotter, while the radiated energy disperses, increasing total entropy. Star formation increases universal entropy, even as it creates localized order. Life itself is an entropy-increasing process. You maintain your complex low-entropy structure by consuming food and radiating heat. Your metabolism increases the universe's total entropy more than your organized body decreases it. Life doesn't violate thermodynamics. It accelerates entropy increase. The arrow of time connects to memory and causation. We remember the past because memory involves recording information, creating low entropy structures, memories, that correlate with past events. This process inevitably increases entropy elsewhere. The future cannot be remembered because it hasn't yet influenced us, hasn't yet left low entropy records in our brains. In black holes, the arrow of time becomes stark. Once past the event horizon, all paths lead to the singularity. Time itself points inward. You cannot avoid the future any more than you can normally avoid tomorrow. The distinction between space and time blurs. What was a direction in space toward the black hole becomes a direction in time toward your future. Cosmologically, the arrow might reverse. If the universe eventually stops expanding and contracts in a big crunch, would entropy decrease? Would time reverse? Most physicists think not. Entropy would continue increasing even during contraction, maintaining time's forward arrow. But we're uncertain. The universe's ultimate fate remains unclear. Some theories propose that entropy's arrow defines time's direction. Time flows from low entropy to high entropy, period. In this view, if somehow a region of the universe had decreasing entropy, time there would flow backward from our perspective. Cause and effect would reverse. This is highly speculative, probably impossible, but it illustrates how deeply entropy and time are connected. The psychological arrow of time, our subjective experience of time flowing, may simply reflect the thermodynamic arrow. Our brains are entropy-increasing systems. Our thought processes require energy flow, heat dissipation, entropy creation. We experience time flowing forward because that's the direction of entropy increase, the direction in which our neural processes operate. The universe began in an extraordinarily special, low entropy state. Why? We don't know. This initial condition problem puzzles cosmologists. Perhaps inflation answers it, a brief period of exponential expansion that smoothed irregularities and set up special initial conditions. But inflation itself requires explanation. Why did inflation occur? What determined its properties? Some physicists invoke the anthropic principle. We observe a low-entropy Big Bang because only such universes develop complex structures like stars, planets, and observers. In high-entropy beginning universes, nothing interesting happens. No one exists to observe them. We see what we see because we can exist only in universes with this particular property. This explanation troubles many scientists. It seems to give up on deeper understanding. Yet if the universe is one of many in a multiverse, each with different properties, anthropic selection might be unavoidable. We inhabit a universe compatible with our existence, just as fish inhabit water. Time's arrow remains mysterious. We understand its connection to entropy, but not why entropy was initially so low. We understand its consequences, but not its ultimate origin. We live immersed in time's flow, unable to reverse it, unable to stop it, carried forward into ever-increasing entropy, toward the heat death, when all gradients equalize and nothing further can happen. But that end lies trillions of years hence. For now, time flows, entropy increases, and the universe continues its journey from the simple past toward the complex, and then the simple again. The Big Bang. 13.8 billion years ago, the universe began, not in an explosion of matter into pre-existing space, but an expansion of space itself, carrying matter and energy with it. Time began at this moment. Asking what happened before the Big Bang is like asking what lies north of the North Pole. The question assumes a framework that doesn't exist. In the beginning, the universe was unimaginably hot and dense. All the matter and energy that would become galaxies, stars, planets, and you occupied a volume smaller than an atom. Temperature exceeded trillions of degrees. No atoms existed. It was too hot for electrons to bind to nuclei. Matter consisted of a plasma of quarks and gluons, the fundamental constituents that would later form protons and neutrons. The universe expanded rapidly, cooling as it grew. Within the first microsecond, quarks combined into protons and neutrons. But it was still far too hot for atoms. For the next 380,000 years, the universe remained an opaque plasma, light scattering constantly off free electrons, unable to travel far before being absorbed and re-emitted. Then, as the universe cooled to about 3000 Kelvin, electrons combined with atomic nuclei, forming the first neutral atoms, mostly hydrogen and helium. This moment, called recombination, allowed light to travel freely for the first time. The universe became transparent. That ancient light still exists. Stretched by the universe's expansion from visible light to microwaves, it fills all of space as the cosmic microwave background radiation, the afterglow of the Big Bang. We detect it in every direction, a faint signal at 2.7 Kelvin, just barely above absolute zero. This light has been traveling through space for 13.8 billion years, its photons journeying from the moment of recombination to arrive at our detectors today. The cosmic microwave background is remarkably uniform, varying by only 1 part in 100,000 across the sky. This uniformity presents a puzzle. How did distant regions of the universe coordinate to have the same temperature? They're so far apart that light hasn't had time to travel between them since the Big Bang. Cosmic inflation provides an answer. in the universe's first fraction of a second, around 10⁻²36 seconds after the Big Bang, space underwent exponential expansion, growing by a factor of at least 10⁻26 in a tiny instant. This inflation expanded a small causally connected region to sizes larger than the observable universe. Regions that seemed too distant to have influenced each other were once close enough to reach thermal equilibrium. Inflation also explains why the universe appears flat rather than curved. Any initial curvature was stretched nearly flat by this enormous expansion. Like inflating a balloon to cosmic scales makes any small region appear flat. The tiny quantum fluctuations in this inflationary field became the seeds of all structure. Regions that were slightly denser attracted more matter, growing denser still, eventually forming the first stars and galaxies. The patterns we see in the cosmic microwave background, those tiny temperature variations, are the blueprints of galaxy clusters and voids, frozen into the light when the universe was 380,000 years old. What caused the Big Bang? We don't know. The question may be unanswerable, perhaps even meaningless. General relativity breaks down at the extreme densities and temperatures of the universe's first moment. Quantum effects become crucial, but we lack a complete theory of quantum gravity to describe this regime. Some theories suggest the Big Bang wasn't the beginning, but a transition. Perhaps the universe undergoes cycles of expansion and contraction, each Big Bang followed eventually by a big crunch, then another bounce into a new expansion phase. Perhaps our universe budded off from a parent universe, a quantum fluctuation that inflated into its own space-time. Perhaps countless universes exist, each with different physical laws, and we inhabit one compatible with our existence. The Big Bang wasn't an explosion in space, but an explosion of space. There was no center, no edge, no outside. Every point in the universe was at the Big Bang. The entire universe emerged from that initial singularity. When we observe distant galaxies receding, they're not moving through space away from us. Space itself is expanding between us and them. This expansion has a speed limit for local motion. Nothing can move through space faster than light, but space itself has no such constraint. Very distant galaxies recede from us faster than light because space between us expands faster than light can traverse it. We will never see these galaxies' current state. We can only observe their ancient past, frozen in light that barely reaches us across the expanding cosmos. In the moments after the Big Bang, the universe underwent rapid nucleosynthesis. Protons and neutrons combined to form light atomic nuclei, deuterium, helium, traces of lithium and beryllium. This process lasted only about 20 minutes. By the time the universe had cooled below the temperatures needed for fusion, about 75% of matter was hydrogen, 25% helium, with trace amounts of other light elements. This predicted ratio matches observations beautifully. Everywhere we look in the universe, we find roughly this proportion of hydrogen to helium in the oldest objects. This concordance provides powerful evidence for the Big Bang model. No other theory explains why the universe should contain these specific ratios of elements. Heavier elements, carbon, oxygen, iron, gold, didn't exist in the early universe. They were forged later in stellar cores and supernova explosions. You are not made of Big Bang matter, you're made of star matter, elements created through nucleosynthesis in earlier stellar generations. The universe's first few hundred million years are called the cosmic dark ages. No stars yet existed to illuminate space. Hydrogen gas filled the universe, with slight variations in density. Gravity pulled this gas into denser clumps. The densest regions collapsed, compressed, heated until nuclear fusion ignited. The first stars were born. These primordial stars were likely massive, hundreds of times the sun's mass, and short-lived, burning intensely and dying in supernova explosions after only a few million years. They had no heavy elements, composed purely of hydrogen and helium. They illuminated the universe for the first time, their ultraviolet radiation ionizing the surrounding hydrogen, creating bubbles of ionized gas that grew and merged. This epoch of rionization gradually cleared the cosmic fog, making the universe transparent to visible light. By about 1 billion years after the Big Bang, the universe was fully Ryanized, appearing much as it does today. Mostly empty space punctuated by stars and galaxies, the Big Bang Theory is not a guess or speculation. It's a robust scientific framework supported by multiple lines of evidence: the cosmic microwave background radiation, the abundance of light elements, the universe's expansion, the evolution of galaxy populations over time, while details remain uncertain, especially regarding the earliest moments. The broad picture is well established, yet profound questions persist. Why is there more matter than antimatter? The Big Bang should have created equal amounts, which would have annihilated, leaving a universe of pure energy. Some asymmetry must exist in the laws of physics, favoring matter over antimatter by a tiny margin. We observe the leftover matter, the small excess that survived mutual annihilation. Why do the fundamental constants have the values they do? Slight changes to the strength of gravity, the mass of electrons, or the charge of protons would create a universe without stars, or without atoms, or without chemistry. The universe appears fine-tuned for complexity, for life. Is this coincidence? Necessity? Anthropic selection from a multiverse? We don't know. The Big Bang marks the beginning of our observable universe, but it may not be the ultimate beginning. Deeper theories may reveal a more fundamental reality from which our space-time emerged. Or the Big Bang may truly be the ultimate origin, time's first moment, before which nothing existed, not even before. For now, we can trace the universe's history back to a fraction of a second after the Big Bang. Beyond that, we speculate, guided by mathematics and imagination, reaching toward understanding the most profound mystery. Why is there something rather than nothing? Cosmic inflation. For the briefest instant, between 10⁻36 and 10⁻32 seconds after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. In this incomprehensibly short time, space expanded by at least a factor of 10.26, possibly much more. Before inflation, the observable universe occupied a region smaller than a proton. Quantum fluctuations dominated. The universe was a seething foam of quantum uncertainty. Then something triggered inflation. Perhaps a scalar field called the inflaton settling into a high-energy state. Perhaps quantum fluctuations themselves, creating the conditions for expansion. During inflation, space expanded faster than light, much faster. The universe doubled in size every 10⁻37 seconds or so. This exponential growth transformed a microscopic patch of space into something vastly larger than our currently observable universe. Why inflation? It solves several cosmological puzzles. First, the horizon problem. Why is the cosmic microwave background uniform across regions that couldn't have communicated? Inflation explains this by expanding a small, thermally equilibrated region to cosmic scales. What we observe as the entire observable universe came from a tiny patch that had time to reach uniform temperature. Second, the flatness problem. Why is space so remarkably flat? Any initial curvature would be stretched nearly flat by inflation's enormous expansion. Like inflating a balloon to cosmic scales makes its surface appear flat to an ant. Third, the monopole problem. Certain theories predict massive magnetic monopoles should have formed in the early universe, but we've never observed one. Inflation dilutes these exotic particles to near non-existence, explaining their absence. Most remarkably, inflation provides a mechanism for structure formation. Quantum fluctuations in the inflaton field got stretched to macroscopic scales during inflation, frozen into the fabric of space as slight variations in density. These variations became the seeds for galaxies, clusters, and the cosmic web. The largest structures in the universe originated as quantum jitters, blown up to astronomical proportions. We see evidence of these primordial fluctuations in the cosmic microwave background, the tiny temperature variations, 1 part in 100,000, match predictions from inflation theory. The statistical properties of these variations, their distribution across angular scales, bear the fingerprints of quantum mechanics operating at cosmic scales. Inflation predicts gravitational waves generated during this expansion should permeate the universe, creating a distinct pattern in the cosmic microwave background's polarization. Detecting this B-mode polarization would provide direct evidence for inflation and reveal the energy scale at which it occurred. Several experiments are searching for this signal, but it's faint and easily confused with foreground contamination. What caused inflation? The honest answer, we don't know. Various models propose different inflaton fields with different properties. We don't know what field drove inflation, what potential it had, or why inflation ended. The slow roll models suggest the inflaton field slowly descended from a high energy state to a lower one, during which inflation occurred. When it reached the bottom, inflation ended, and the inflaton's energy converted to matter and radiation, reheating the universe. Eternal inflation is an intriguing consequence of some inflation models. If inflation is driven by quantum fluctuations, it might never completely end. While inflation stops in some regions, allowing normal cosmic evolution, it continues elsewhere. These inflating regions produce new universes, pocket universes like ours, in an eternally inflating multiverse. Each pocket universe might have different physical laws, different constants, different numbers of dimensions. We observe the laws we do because we exist in a pocket compatible with our existence. This anthropic explanation troubles many scientists, but naturally emerges from certain inflation models. Inflation makes testable predictions, distinguishing it from pure speculation. The prediction of a nearly flat universe was confirmed by measurements of the cosmic microwave background. The prediction of a nearly scale-invariant spectrum of density fluctuations was confirmed. The predicted Gaussian statistics of fluctuations were confirmed. Inflation has passed test after test, yet alternatives exist. Cyclic models propose that the universe undergoes repeated cycles of expansion and contraction without inflation. String theory gas cosmology suggests the Big Bang arose from colliding higher dimensional branes. These alternatives make different predictions, but inflation remains the dominant paradigm because of its explanatory power and confirmed predictions. Inflation transforms our understanding of the observable universe. The cosmos we see, billions of light years across, containing trillions of galaxies, occupies an infinitesimally small patch of the larger universe created during inflation. Beyond our cosmic horizon lie regions forever beyond our view, regions that inflated from the same primordial quantum foam, but have evolved differently. If eternal inflation is correct, our universe is one bubble in an infinite cosmic froth, each bubble a universe unto itself. The true cosmos would be unimaginably vaster than the portion we can observe, perhaps infinite, perhaps containing every possible variation of physical laws. This is heady stuff, bordering on philosophy. Yet it follows from taking inflation seriously, extrapolating from well-tested physics to its logical conclusions. We may never know if eternal inflation is real or if pocket universes exist. They might be forever beyond observational reach. But the possibility reshapes how we think about our place in the cosmos. Inflation lasted perhaps 10^32 seconds. In that fleeting instant, the structure of the observable universe was determined. Every galaxy, every star, every atom traces its existence to quantum fluctuations during that brief moment at the beginning of time. Dark matter. Most of the universe is invisible. When astronomers calculate how much matter should exist based on gravitational effects, they find 5 times more than the matter we can see. This hidden mass is dark matter. It doesn't emit, absorb, or reflect light, revealing itself only through gravity. Evidence for dark matter is overwhelming. In the 1930s, Fritz Zwicky noticed that galaxies in the Coma cluster moved too fast. Their speeds suggested far more mass than visible stars contained. Either Newtonian gravity was wrong, or unseen matter provided additional gravitational pull. In the 1970s, Vera Rubin studied galaxy rotation curves, measuring how fast stars orbit galactic centers at various distances. According to visible matter distributions, stars far from centers should orbit slowly. Instead, they orbit as fast as stars closer in. Galaxies rotate as if embedded in massive halos of invisible matter extending far beyond visible edges. Gravitational lensing provides another line of evidence. Mass bends space-time, curving light paths. When we observe distant galaxies through galaxy clusters, their images are distorted and magnified by the cluster's gravity. By measuring this distortion, we can map the cluster's mass distribution. The results consistently show far more mass than visible matter accounts for. The dark matter halo, the Bullet cluster, provides particularly striking evidence. Two galaxy clusters collided, passing through each other. The visible matter, hot gas, interacted and slowed down, piling up between the clusters. But gravitational lensing reveals that most mass passed straight through, continuing undisturbed. Dark matter, which interacts only gravitationally, moved right through the collision while normal matter got stuck. What is dark matter? We don't know. It's not made of atoms or any particles in the standard model of particle physics. It's something else, something that interacts gravitationally, but not electromagnetically. Leading candidates include WIMPs, weakly interacting massive particles, axions, and sterile neutrinos. WIMPs would be heavy particles left over from the Big Bang, moving slowly through space, occasionally passing through ordinary matter. Despite decades of sensitive experiments deep underground, we haven't detected WIMPs directly. Either they're rarer than expected, or dark matter is something else. Axions are hypothetical ultralight particles that might have been produced in vast quantities in the early universe. Several experiments are searching for axions, but detection is challenging because they interact so weakly with ordinary matter. Some theories propose dark matter consists of primordial black holes, small black holes formed in the early universe. But observations constrain how many such black holes could exist. They probably can't account for all dark matter. Modified gravity theories like MOND, modified Newtonian dynamics, attempt to explain observations without dark matter by proposing that gravity behaves differently at low accelerations. MOND successfully explains galaxy rotation curves, but struggles with other observations like gravitational lensing and cosmic microwave background patterns. Most physicists favor dark matter over modified gravity. Dark matter played a crucial role in structure formation. After recombination, normal matter was dispersed uniformly, coupled to photons by electromagnetic interactions. But dark matter, unaffected by photons, began collapsing gravitationally immediately. Dark matter halos formed first, their gravity pulling normal matter into them. Galaxies formed within these dark matter scaffolds. Computer simulations of cosmic evolution include dark matter, modeling how its gravity shapes structure over billions of years. These simulations reproduce observed galaxy distributions, cluster formations, and the cosmic web's filamentary structure. Without dark matter, simulations fail to match observations. Dark matter appears to be cold, moving slowly relative to light speed. Hot dark matter, like neutrinos, moves near light speed and wouldn't clump enough to form galaxies. Cold dark matter clumps efficiently, forming the gravitational wells where galaxies coalesce. The Milky Way swims through a halo of dark matter. Perhaps 10-11 solar masses of dark matter surrounds our galaxy, extending well beyond the visible disk. Dark matter particles constantly pass through Earth, through you, billions every second. But they interact so weakly that they pass through matter like ghosts, undetectable except through gravity. Direct detection experiments deep underground try to catch dark matter particles colliding with atomic nuclei. These experiments require extreme sensitivity and massive shielding to exclude background radiation. So far, no confirmed detections, though occasional tantalizing hints later proved false. The Large Hadron Collider searches for dark matter by trying to create it. If dark matter particles can be produced in high-energy collisions, they would carry away energy and momentum, detectable as missing energy in collision debris. Again, no confirmed discoveries yet. Dark matter's invisibility frustrates us. It's everywhere, It outweighs visible matter 5 to 1. It shapes cosmic structure, yet we can't identify it. It's like knowing a room contains an elephant, but being unable to see, hear, or touch it. Only inferring its presence from footprints and the way furniture moves aside. Some physicists speculate that dark matter might interact with itself through unknown forces, creating dark atoms or dark molecules in a hidden sector of physics parallel to our own. Others suggest dark matter might occasionally annihilate, producing gamma rays we might detect from galactic centers. These ideas remain speculative. Dark matter might not be a single thing. Perhaps multiple types of dark matter exist, just as normal matter includes many particle types. The universe might be more complex than we imagine, with invisible realms of physics operating alongside the visible. For now, dark matter remains one of physics' greatest mysteries. Ubiquitous, yet unidentified. Crucial, yet incomprehensible. It reminds us how much we don't know about the universe's composition. Most of the universe is made of something we've never detected except through its gravitational pull. Reality is stranger and fuller than we ever imagined. Dark energy. In 1998, 2 teams of astronomers studying distant supernovae made a shocking discovery. The universe's expansion isn't slowing down, it's speeding up. This acceleration requires some kind of energy permeating space itself, pushing everything apart. We call it dark energy, though we have no idea what it is. Before this discovery, cosmologists expected expansion to slow due to gravity. Matter attracts matter, so gravitational pull should decelerate the universe's expansion, possibly eventually stopping it, or even reversing it into a big crunch. Instead, observations showed distant supernovae were dimmer than expected, meaning they were farther away, meaning space had expanded more than predicted. Expansion was accelerating. This result was so unexpected that both teams checked and rechecked their data before announcing it. But the findings held. Follow-up observations confirmed the acceleration. In 2011, the discovery earned the Nobel Prize in Physics. Dark energy accounts for about 68% of the universe's total energy density. Dark matter accounts for about 27%. Normal matter, everything we can see, all atoms, all stars, all galaxies, makes up only 5%. We understand the nature of only the smallest slice of the universe. What is dark energy? The simplest explanation is Einstein's cosmological constant, a constant energy density of space itself. Empty space has energy. The more space exists, the more dark energy there is. As the universe expands, more space comes into existence, bringing more dark energy, which accelerates expansion further, creating even more space and so on. Einstein originally introduced the cosmological constant to make the universe static, balancing gravity's attraction. When Hubble discovered the universe expands, Einstein called the cosmological constant his greatest blunder. Ironically, it turns out the constant exists, but with a value that accelerates expansion rather than preventing it. Quantum field theory predicts that empty space should have energy from virtual particle fluctuations. But when physicists calculate how much energy the vacuum should have, they get an absurdly large number. 120 orders of magnitude larger than observed dark energy density. This is the worst prediction in physics history, a discrepancy so enormous it suggests we're missing something fundamental. Why is dark energy's observed value so small, yet non-zero? This fine-tuning problem bothers physicists. A larger dark energy density would prevent structure formation. Galaxies, stars, planets couldn't form. A zero value seems more natural than the tiny but non-zero value we observe. Why does space have just enough energy to accelerate expansion without tearing everything apart? Alternative theories propose that dark energy isn't constant, but varies over time. Quintessence models involving a dynamical field that changes as the universe evolves. This could explain why dark energy's density is comparable to matter density now. Perhaps the two were always related, their evolution linked, or maybe our theory of gravity breaks down at cosmological scales. Perhaps Einstein's equations need modification. Many alternative gravity theories have been proposed, but most struggle to explain observations without introducing something equivalent to dark energy anyway. Dark energy has profound implications for the universe's fate. If it remains constant, the universe will expand forever, accelerating eternally. Galaxies beyond our local group will recede faster than light, disappearing beyond our cosmic horizon. Eventually, in trillions of years, only our local group's merged galaxy will remain visible. The night sky will darken. Future civilizations will see an apparently empty universe, unable to discover that billions of other galaxies once existed. Eventually, even stars will die. The last star will flicker out perhaps 100 trillion years from now. Black holes will be the only remaining massive objects, slowly evaporating through Hawking radiation over unimaginable timescales. After 10 or 100 years, even black holes will have evaporated. Only diffuse radiation will remain, growing ever more dilute as space expands without bound. This is the heat death. Maximum entropy, no remaining gradients, no energy available to do work. Nothing can happen anymore. The universe becomes dark, cold, and empty, expanding eternally into an infinite future of perfect stagnation. If dark energy strengthens over time, the Big Rip becomes possible. Accelerated expansion could eventually overcome gravity at smaller and smaller scales, first tearing apart galaxy clusters, then galaxies, then solar systems, then planets, eventually atoms themselves. The universe would shred itself, space-time expanding so rapidly that nothing remains bound together. If dark energy weakens or reverses, expansion could slow and eventually reverse, leading to the Big Crunch. The universe would contract, galaxies would blue shifts as they approached, eventually colliding. Matter would compress, temperatures would rise, and the universe would collapse back into a singularity, perhaps followed by a new Big Bang in an endless cycle. Current observations suggest dark energy is constant or nearly constant. Consistent with the cosmological constant, the expansion rate appears steady. If this holds, the heat death scenario seems most likely. We live in an era when the universe is still vibrant, still rich with structure and activity. But this is temporary. In the deep future, darkness and cold will prevail. Dark energy represents a vast gap in our understanding. It dominates the universe's energy budget, determines its ultimate fate, yet we can't explain what it is or why it exists. Every explanation requires fine-tuning or introduces new mysteries. The universe is accelerating toward an unknowable future, driven by energy we don't understand, toward a fate we can only speculate about. Like dark matter, dark energy humbles us. It reveals how limited our knowledge remains. We've mapped the cosmos, measured its age, traced its history, yet most of it remains mysterious. The universe is mostly invisible matter held together by gravity, permeated by invisible energy pulling it apart. We inhabit a cosmos whose fundamental composition remains unknown. The multiverse. Does our universe exhaust reality, or is it one among many? The multiverse idea suggests countless other universes exist, perhaps with different physical laws, different constants, different dimensionalities. Some of these universes might be similar to ours. Others might be unimaginably alien. Several independent lines of reasoning lead to multiverse proposals. Eternal inflation suggests inflation never completely ends, continually creating new pocket universes. Our Big Bang would be one bubble in an endlessly inflating cosmos. Each bubble a separate universe with potentially different properties. String theory allows approximately 10⁵00 different possible vacua, stable configurations with different physical laws. If these all exist somewhere, they would form a landscape of universes, each occupying its region of a vast multiverse. Our universe's laws wouldn't be fundamental. They'd be local conditions like Earth's climate. Not universal truths, but contingent facts. The many worlds interpretation of quantum mechanics proposes that every quantum measurement spawns new branches of reality. Each possible outcome occurs in some branch. From this view, countless parallel universes exist, one for each possible quantum history. Every moment, reality branches into incomprehensibly many parallel versions. These different multiverse proposals are not the same theory. Eternal inflation's pocket universes differ from quantum mechanical branches. The string landscape differs from both. Yet all suggest our universe isn't unique. The anthropic principle becomes relevant in multiverse scenarios. If countless universes exist with varying properties, we necessarily observe one compatible with our existence. The fine-tuning of physical constants. The seemingly miraculous adjustments that allow stars, atoms, and life might simply reflect selection bias. We exist in a universe hospitable to our existence because no observers arise in inhospitable universes. This explanation troubles many scientists. It seems to abandon the search for deeper explanations. Instead of asking, why are the constants fine-tuned? It says, they're not. Countless universes have different constants, and we're in one that works. It feels like giving up. Yet, if the multiverse is real, anthropic reasoning becomes necessary. Not everything requires explanation if it's selected from a vast ensemble of possibilities. Demanding explanations for anthropically selected features would be like asking why Earth has water and oxygen. Not because physical laws require it, but because life couldn't arise to ask the question on planets without these features. Can we ever test multiverse theories? Direct observation seems impossible. Other universes, if they exist, lie beyond our ability to detect. But multiverse theories make statistical predictions. If we live in a typical universe from some ensemble, our observations should reflect typical properties from that ensemble. Deviations from typicality would count as evidence against the multiverse model. Some cosmologists search for bruises on the cosmic microwave background, cold spots that might indicate our universe collided with another bubble universe during inflation. No confirmed detections exist yet, and most theorists think collisions would be rare. The multiverse challenges our notion of what science can explain. Traditional science seeks universal laws explaining all observations. But if our observations reflect local conditions in one universe among many, universal explanations may not exist. Science would become more like geography, mapping what exists rather than explaining why it must be so. Critics argue that untestable multiverse theories aren't science but metaphysics. If we can never observe other universes, why believe in them? Proponents respond that theories should be judged by their explanatory power and coherence, not just direct testability. General relativity predicted black holes long before we could observe them. The multiverse might be similar, a valid consequence of theories even if direct observation is impossible. Some find the multiverse concept disturbing. It suggests our universe isn't special, our existence not unique. If every possibility occurs in some universe, nothing is truly remarkable. Every choice you make, you also don't make in another branch. Every version of history unfolds somewhere. This can feel nihilistic, stripping meaning from existence. Others find it awe-inspiring. If the multiverse exists, reality is far vaster than the observable universe. The true cosmos would be infinite in a much deeper sense. Not just endless space, but endless possibility. Every potential realization actualized somewhere. The multiverse remains speculative. We have theories suggesting it exists, but no definitive evidence. It might be real, or it might be an artifact of incomplete understanding. Perhaps future theories will avoid multiverse implications. For now, we can observe only our universe. We measure its properties, trace its history, probe its structure. Whether beyond our cosmic horizon lie other universes, or simply more of the same, we may never know. The question touches the limits of science, perhaps the limits of knowability itself. But speculation has value. The multiverse idea forces us to question assumptions. It challenges us to think carefully about what scientific explanation means. It reveals that our intuitions, shaped by experience in one universe, might mislead us about the full scope of reality. Perhaps someday, distant descendants with technologies we can't imagine will find evidence of other universes. Or perhaps the question will remain forever beyond empirical reach. a philosophical puzzle rather than a scientific one. Either way, the multiverse concept expands our vision, reminding us that what we see might represent only a fragment of what exists. The end of the universe. The universe had a beginning. Will it have an end? The answer depends on dark energy's nature and the universe's geometry. Several possible fates await, each fascinating and terrible in its own way. Heat death is the most likely scenario based on current observations. If dark energy remains constant, the universe will expand forever, accelerating indefinitely. Galaxies beyond our local group will recede beyond the cosmic event horizon, their light never reaching us again. Star formation will continue for trillions of years, but gas supplies are finite. Stars will exhaust available hydrogen. New stars will stop forming. Existing stars will die one by one. Red dwarfs lasting trillions of years will be the last to go, fading slowly into cold black dwarfs. After 10-14 years, galaxies will be full of stellar remnants, white dwarfs, neutron stars, black holes, and dissipating gas. Planets will be ejected from their orbits through gravitational interactions or will spiral into stellar remnants. Around 10-19 years, galaxies themselves will evaporate. Stars will be ejected from their galaxies through random gravitational encounters, wandering alone through intergalactic space. Others will fall into central black holes. By 10-40 years, black holes will dominate. They'll grow through occasional mergers, absorbing any remaining matter. But even black holes aren't eternal. Stephen Hawking showed that black holes emit radiation due to quantum effects. They slowly evaporate, with smaller holes evaporating faster. A stellar mass black hole takes about 1067 years to evaporate completely. Supermassive black holes require 10-100 years or more. Eventually, even the largest black holes will vanish in final bursts of radiation. After perhaps 10-100 years, nothing remains but diffuse photons, neutrinos, and other particles spreading ever thinner as space expands. Temperature approaches absolute zero. No gradients exist, no energy concentrations capable of doing work. This is heat death. Maximum entropy, ultimate stillness. Nothing can happen because nothing is different from anything else. Time becomes meaningless because no change occurs. The universe doesn't die violently. It fades into eternal darkness. Big Rip occurs if dark energy strengthens over time. Accelerated expansion would increase, eventually overcoming all binding forces. First, galaxy clusters would tear apart. Perhaps 200 billion years from now. Then galaxies themselves would shred, 60 million years before the rip. Then solar systems would dissolve, 3 months before the end. Finally, molecules, atoms, and even atomic nuclei would be torn apart as space expands faster than the forces holding them together. Space-time itself might tear, ending everything in a catastrophic shredding of reality. This scenario requires phantom energy with exotic properties. Current observations don't support it. Dark energy appears to be the cosmological constant or something close, but we can't rule it out entirely. Big crunch occurs if dark energy weakens or gravity eventually overcomes expansion. The universe would stop expanding and begin contracting. At first, imperceptibly, then faster. Galaxies would blue shift as they approached. Eventually, galaxies would collide and merge. As contraction continues, temperatures would rise. The cosmic microwave background would blue shift from microwaves to infrared, then visible light, then ultraviolet and X-rays. Space would glow, then blaze. Matter would disintegrate in the heat. Eventually, the universe would collapse into a singularity, a reverse Big Bang, perhaps followed by a new Big Bang in a cyclic model. Some versions of string theory allow cyclic universes that bounce between Big Bangs and Big Crunches indefinitely. Each cycle might last trillions of years with slightly different properties, an eternal rhythm of expansion and contraction. Big Freeze is similar to heat death, but emphasizes the universe becoming infinitely cold and diffuse, rather than reaching maximum entropy. It's really the same scenario, viewed through a different lens. Eternal expansion leading to darkness and cold. False vacuum decay is a more exotic possibility. Perhaps the Higgs field isn't in its lowest energy state, but in a metastable false vacuum. Quantum tunneling could allow a region of space to suddenly drop into the true vacuum, releasing enormous energy. This transition would expand at light speed in a bubble of true vacuum, destroying everything in its path, rewriting physical laws within the bubble. We couldn't see it coming. The bubble would arrive traveling at light speed, giving no warning. Everything would simply cease to exist in an instant as the bubble's wall passed through. From our perspective, existence would end without notice. This scenario is speculative. Most physicists think the Higgs vacuum is stable, or at least stable enough to last far longer than the universe's current age. But we can't be absolutely certain. Vacuum instability related to black holes is another concern. The extreme conditions near black hole singularities might trigger vacuum decay, creating bubbles of catastrophic instability, but calculations suggest this is unlikely. Proton decay. Some grand unified theories predict that protons decay with half-lives around 10^34 years. If true, all atomic matter would slowly disappear as protons transformed into lighter particles and energy. By 1040 years, all atoms would be gone, leaving only radiation and leptons. This would accelerate the heat death scenario. Despite extensive searches, we've never observed proton decay. Either protons are stable, or their half-life exceeds 10^34 years. The standard model assumes protons are perfectly stable, but grand unified theories suggest otherwise. We're still uncertain. Big bounce models propose that quantum gravity effects prevent singularities. Instead of collapsing into a singularity, a contracting universe would reach a minimum size, then bounce into a new expansion phase. This avoids the infinities of classical Big Bang cosmology, replacing them with a transition from contraction to expansion. Each bounce might reset the universe, creating new structures, perhaps new physical laws. Information from previous cycles might be erased, making each cycle essentially a new beginning. Or perhaps some information survives, carried through the bounce as seeds for new structure. These scenarios span unimaginable timescales. The universe is currently 13.8 billion years old, a cosmic infant. The first stars will die after 100 trillion years, more than 7,000 times the universe's current age. Black holes will evaporate after 10,100 years, incomprehensibly longer. Heat death might not complete until 10,000 years or more. Yet even these vast times are finite. Given infinite time, any scenario with non-zero probability becomes certain. Quantum fluctuations might spontaneously create new Big Bangs from empty space, given infinite time. The heat death might be interrupted by random quantum events generating new universes, or perhaps time itself ends. If the universe contracts to a singularity, space-time ceases. If vacuum decay rewrites physics, time as we know it might not exist in the new vacuum. Time might be finite in duration, with a definite ending beyond which after has no meaning. The universe's end, whatever form it takes, lies inconceivably far in the future. The Sun will die in 5 billion years. The Milky Way will merge with Andromeda in 4 to 5 billion years. These events, vast by human timescales, are trivial compared to the universe's ultimate fate. But eventually, somehow, this cosmic story reaches its conclusion. Whether in fire or ice, in tearing or fading, in collapse or eternal expansion, the universe's current form is temporary. Everything that exists, every galaxy, every star, every atom, will pass away. All structures are transient. All complexity is temporary. The universe moves inexorably towards simplicity, towards stillness, toward an ending we can barely imagine. Yet in this moment, life exists. Consciousness arises. The universe beholds itself through our eyes, contemplates itself through our minds. For a brief span, matter has organized into patterns complex enough to wonder, to question, to understand. This flickering moment of awareness amid eternity is precious beyond measure. The anthropic universe. The universe seems fine-tuned for life, Change any of several fundamental constants by even tiny amounts, and the universe becomes sterile. No stars, no planets, no chemistry complex enough for life. If the strong nuclear force was slightly weaker, atomic nuclei couldn't form. No elements beyond hydrogen would exist. If slightly stronger, hydrogen would fuse too easily, and stars would burn out in moments. If the electromagnetic force was slightly different, chemical bonds couldn't form. No molecules, no chemistry, no life. Water wouldn't be liquid at Earth's temperature. Carbon chemistry wouldn't work. If gravity was stronger, stars would collapse quickly, living only briefly. If weaker, stars couldn't form. Gas clouds wouldn't compress enough to ignite fusion. Either way, no stable stars for planets to orbit. No long-term energy sources for life. The ratio of the electron's mass to the proton's mass appears precisely calibrated. Change it slightly, and chemistry changes dramatically. Complex molecules couldn't form. The periodic table would look entirely different, probably incapable of supporting life's chemistry. The cosmological constant, dark energy's strength, appears absurdly fine-tuned. If it were larger by even a factor of 10, the universe would have expanded so rapidly that galaxies couldn't form. Matter would never clump enough to create stars. If much smaller or negative, the universe might have recollapsed before stars could form. The initial density fluctuations in the early universe, those tiny variations that seeded galaxy formation, had to be just right. Too small, and structure wouldn't form. Too large, and the universe would collapse into black holes. The actual value sits in a narrow range, permitting both structure formation and long-term stability. These coincidences puzzle scientists. Is the universe designed for life? That would require a designer, stepping outside scientific explanation. Is it chance? With so many parameters requiring fine-tuning, pure chance seems inadequate. The anthropic principle offers an answer. We observe a life-permitting universe because only such universes produce observers. In a lifeless universe, no one exists to notice. Selection bias explains the apparent fine-tuning. We couldn't observe any other type of universe. This explanation only satisfies if many universes exist with varying properties. In a multiverse with countless universes having different physical constants, some will randomly happen to permit life. We necessarily find ourselves in one of those rare life-permitting universes. Without a multiverse, anthropic reasoning feels empty. It answers, why is the universe life-permitting? With, because otherwise we wouldn't be here to ask. True, but unsatisfying. It doesn't explain, it merely restates the observation. With a multiverse, anthropic reasoning gains explanatory power. The question becomes, why do we observe these particular constants? Answer: because we exist in a universe from the subset that permits observers. This is genuine explanation if the multiverse exists. Some constants might not be as finely tuned as they appear. Perhaps different combinations of constants allow life. Carbon-based chemistry might not be the only path to complexity. Silicon-based life or exotic life based on entirely different chemistry might be possible in universes with different constants. We assume life requires our chemistry because it's all we know, or perhaps constants aren't independent. Deeper theories might relate them, reducing the fine-tuning problem. String theory suggests all constants emerge from the geometry of extra dimensions. Perhaps there are fewer free parameters than we think, and the apparently independent constants are connected by underlying principles we don't yet understand. The anthropic principle has limits. It can't explain everything. If we observed a universe far more hospitable to life than necessary, say, every planet teemed with life, anthropic reasoning wouldn't explain this. It only explains why the universe meets the minimum requirements for observers. Some scientists embrace the anthropic principle enthusiastically. Others reject it, viewing it as giving up on deeper explanations. The debate continues, unresolved, touching fundamental questions about scientific explanation and the universe's nature. The fine-tuning problem reveals how precarious existence is. The The universe balances on a knife's edge. Small changes in fundamental constants would render it sterile. We exist in a narrow band of possibility, in a universe that, by chance, design, or anthropic selection, happens to permit our existence. This should inspire both humility and wonder. Humility because we're profoundly lucky, beneficiaries of extraordinary coincidence. Wonder because the universe somehow arrived at precisely the configuration needed for matter to organize into galaxies, stars, planets, and eventually life complex enough to contemplate these questions. Perhaps the anthropic principle is temporary scaffolding, useful until we discover deeper explanations. Or perhaps it's a permanent feature of cosmology, a recognition that some questions answer themselves through the fact of our existence. Either way, it forces us to think carefully about what we can and cannot explain, and why we observe what we do. The universe we observe is the only universe we could observe. This tautology might be profound truth or meaningless philosophy, depending on whether other universes exist. For now, we can only study this one, marvel at its properties, and wonder whether its life-permitting character requires explanation beyond our existence to observe it. Are we alone? Earth teems with life, millions of species filling every available niche. Life exists in boiling hot springs, in frozen Antarctic lakes, deep underground, high in the atmosphere, in acidic pools, in radioactive waste. Life is tenacious, adaptable, persistent. This suggests life might arise wherever conditions permit. With trillions of planets in the galaxy, many orbiting in habitable zones, life elsewhere seems probable. Yet we've found no evidence, no signals from alien civilizations, no signs of technological activity. The universe seems silent. This is the Fermi paradox, named after physicist Enrico Fermi, who asked, "Where is everybody?" The paradox arises from the contrast between the high probability of life existing elsewhere and the complete absence of evidence for it. Several possibilities resolve the paradox. Perhaps life is rare. Despite Earth's example, maybe the origin of life requires extraordinarily unlikely circumstances. The right chemicals, the right energy sources, the right environmental conditions must align in ways we don't understand. If life's origin is sufficiently improbable, Earth might be unique or nearly so. Perhaps simple life is common, but complex life is rare. Bacteria might fill countless worlds, but multicellular complexity might require additional unlikely steps. Earth took over 3 billion years to evolve from simple cells to multicellular organisms. Most of life's history involved only single cells. Perhaps this transition is unusually difficult. Perhaps intelligent life is rare. Evolution doesn't inevitably lead to intelligence. For billions of years, Earth had life but no technology. Intelligence might be an unlikely accident, not an inevitable outcome. We might live in a galaxy teeming with microbial life, but devoid of civilizations. Perhaps intelligent civilizations are common but short-lived. Technological species might inevitably destroy themselves through war, environmental collapse, or other catastrophes before spreading through the galaxy. The window between developing technology and extinction might be brief. Perhaps civilizations exist, but remain silent. They might listen without broadcasting, avoiding detection for security reasons. Announcing your presence to unknown cosmic neighbors might be dangerous. Better to observe quietly than to reveal yourself. Perhaps they communicate in ways we don't recognize. We search for radio signals, but advanced civilizations might use quantum communication, neutrino beams, or methods we can't imagine. We might be looking in the wrong wavelengths, using the wrong assumptions. Perhaps they're too far away. Even if many civilizations exist, the vast distances between stars make contact difficult. Light speed limits prevent real-time communication over interstellar distances. Civilizations might exist, but remain isolated by the tyranny of cosmic distance. Perhaps we're early. Stars will shine for trillions of years. Life might be just beginning in the universe. Perhaps we're among the first civilizations to arise, preceding rather than following the galaxy's awakening to intelligence. Or perhaps, and this is the loneliest possibility, We're alone. Earth might be the only living world. Consciousness, a unique accident that occurred once and will never recur. The universe might be vast, ancient, and filled with potential. Yet we might be its only voice, its only eyes, its only awareness. We search nonetheless. SETI, Search for Extraterrestrial Intelligence, projects scan the sky for artificial signals. Radio telescopes listen for patterns that couldn't arise naturally. Narrow band signals, repeating pulses, complex modulations. We've heard tantalizing hints. The WOW signal detected in 1977 was a strong, narrow band radio signal that lasted 72 seconds and never repeated. Its source remains unknown. Fast radio bursts, intense but brief radio pulses from distant galaxies. Puzzle astronomers. Most are probably natural phenomena, but we're not certain. We search for biosignatures, atmospheric gases that indicate life. Oxygen, methane, and other molecules in planetary atmospheres might reveal biological activity. The James Webb Space Telescope can analyze exoplanet atmospheres, searching for these signs. We send messages outward. The Arecibo message broadcasted toward globular cluster M13 in 1974, though it won't arrive for 25,000 years. Pioneer and Voyager spacecraft carry plaques and golden records showing our location and culture, messages in bottles cast into the cosmic ocean. Some warn against active messaging. Broadcasting our presence might be dangerous if hostile civilizations exist. Others argue we've already revealed ourselves. Radio and television signals have leaked into space for decades. Any nearby civilization would already know we're here. The Drake equation attempts to estimate the number of communicating civilizations in the galaxy. It multiplies factors like the star formation rate, fraction of stars with planets, fraction of planets that are habitable, fraction where life arises, fraction where intelligence evolves, and the lifetime of technological civilizations. Depending on the values used, the Drake equation suggests anywhere from 0 to millions of civilizations. We don't know most parameters with any confidence. The equation is more useful as a framework for thinking about the question than as a calculator producing answers. Mars once had liquid water. Ancient riverbeds, lake beds, and ocean shores mark its surface. If life arose there, it might persist underground, where liquid water could still exist. Multiple missions search for Martian biosignatures or fossils of ancient life. Europa and Enceladus, moons of Jupiter and Saturn, have subsurface oceans. Plumes of water shoot into space from Enceladus. These moons might harbor life in their dark oceans, ecosystems based on chemical energy rather than sunlight, similar to Earth's deep-sea hydrothermal vents. Titan, Saturn's largest moon, has lakes of liquid methane. Some speculate about exotic life forms using methane as a solvent instead of water, operating at temperatures 180 degrees below 0 Celsius. Such life would be profoundly different from Earth life, but perhaps possible. If we find life elsewhere, even microbial life, it would revolutionize our understanding. One data point, Earth, tells us only that life is possible. 2 data points would tell us whether life is common or rare. If life arose independently on Mars or Europa, it suggests life emerges readily wherever conditions permit. And if we find intelligent life, everything changes. We'd know we're not alone. We'd have someone to share the cosmos with, someone to communicate with across the light years. Even if communication took decades or centuries per exchange, we'd know other minds exist. Other civilizations gaze at the same stars. For now, we search and listen, sending our messages and hoping for reply. The silence continues, vast and ambiguous. We don't know if we're alone or simply haven't looked long enough, if we're too early or if others are too far away. The question remains open, perhaps the most profound question we can ask. Are we the universe's only voice? Or merely one among countless others scattered through the cosmic night? Consciousness and the cosmos. You are the universe become aware of itself. The atoms in your body were forged in stellar cores, scattered by supernovae, reassembled into planets, organized into cells, and somehow, mysteriously, arranged into patterns that produce consciousness. What is consciousness? Despite centuries of philosophy and decades of neuroscience, we cannot fully answer this question. We know brain activity correlates with conscious experience. We know anesthesia disrupts consciousness. We know damage to specific brain regions affects specific aspects of awareness. Yet we don't understand how physical processes generate subjective experience. The hard problem of consciousness. Why does the neural firing in your brain produce the felt experience of seeing red, hearing music, feeling pain? Why is there something it's like to be you, a philosophical zombie, a being physically identical to you but lacking subjective experience? Seems conceivable. What makes you different? Why does your brain generate inner experience while most matter doesn't? Some philosophers argue consciousness is fundamental, not reducible to physical processes. In this view, consciousness might be a basic feature of reality like mass or charge, present to varying degrees in different systems. Perhaps even electrons possess rudimentary consciousness. This is panpsychism, the idea that mind is ubiquitous and human consciousness is just a complex manifestation of a universal property. Others argue consciousness is purely physical, an emergent property of complex information processing. Just as temperature emerges from molecular motion, consciousness emerges from neural computation. We don't understand how yet, but in principle, consciousness should be explicable through neuroscience. Integrated information theory proposes that consciousness corresponds to integrated information. Roughly, how much a system processes information as a unified whole rather than as separate parts. Your brain integrates vast amounts of information across different regions, creating a unified conscious experience. Systems with high integrated information are highly conscious. Systems with low integration are minimally conscious or unconscious. Global workspace theory suggests consciousness arises when information becomes globally available across brain regions. Unconscious processing occurs in specialized modules. Conscious awareness happens when information enters a global workspace accessible to multiple systems. Attention, memory, decision-making, language. These theories might be right, wrong, or partially correct. Consciousness research remains in early stages, struggling with fundamental questions. Can we ever fully understand consciousness? Or does understanding require something consciousness cannot achieve? Stepping outside itself to observe objectively, the measurement problem in quantum mechanics connects provocatively to consciousness. Some interpretations suggest observation collapses the wave function. Does this require consciousness? Most physicists say no. Any physical interaction constitutes measurement. But a minority suggests consciousness plays a fundamental role in quantum mechanics, that observer and observed cannot be cleanly separated. Roger Penrose and Stuart Hameroff propose that consciousness involves quantum processes in brain structures called microtubules. Quantum coherence in neurons might explain consciousness's unity and specific character. Most neuroscientists are skeptical. Brains seem too warm and wet for quantum coherence to persist. But the idea remains intriguing, suggesting consciousness might connect to the quantum foundations of reality. If consciousness is fundamental, it transforms our cosmic perspective. The universe wouldn't be dead matter accidentally producing conscious observers. It would be inherently experiential, matter and mind interwoven from the beginning. The Big Bang would be not just an explosion of matter, but an explosion of potential experience. Or perhaps consciousness is rare and precious, an unlikely arrangement of matter that occurred at least once, here, now, in you. In this view, most of the universe is dark, unconscious, mechanical. Consciousness arises only in special configurations like brains, fleeting islands of awareness in an unconscious cosmos. Either way, your consciousness is remarkable. You process information from your senses, integrate it into coherent experience, generate thoughts and emotions, make decisions, reflect on your own existence. You're a pattern of matter that knows itself, that questions, that wonders. You're also connected to the cosmos in intimate ways. The calcium in your bones came from exploding stars. The water in your cells formed in molecular clouds between stars. The carbon in your DNA was created in stellar cores. You're not separate from the universe. You're a part of it, a temporary configuration of cosmic matter and energy. Your consciousness might be the universe's way of knowing itself. Through your eyes, the universe observes its own grandeur. Through your mind, it contemplates its own nature. Through your wonder, it appreciates its own beauty. You are the cosmos examining itself, asking questions about its own existence. This perspective shift changes everything. You're not a tiny, insignificant speck in a vast, uncaring universe. You're the universe manifesting consciousness, awareness arising from matter, the cosmos becoming self-aware. Your existence gives the universe meaning, purpose, value. Without consciousness, all those galaxies, stars, and planets would be pointless, unobserved, unappreciated. Some find this perspective empowering. You matter because you're how the universe matters. Your thoughts, experiences, and actions have cosmic significance. You're participating in the universe's grand experiment of self-awareness. Others find it humbling. You're not the center of creation, but one instance of consciousness among potentially many. Your individual existence is temporary, a brief flicker in cosmic time. Yet you're part of something vaster, connected to everything through shared atomic origins and physical laws. Perhaps both responses are appropriate: wonder and humility, significance and insignificance. These seeming opposites coexist in the cosmic perspective. You're simultaneously tiny and vast, temporary and connected to eternity, insignificant and profoundly meaningful. Seeing Earth from space. Astronauts describe a transformative experience when seeing Earth from space. The overview effect. Our planet appears as a fragile blue marble, suspended in black void, without borders, unified, precious. From space, Earth's atmosphere is a thin blue line, a delicate shell protecting life from vacuum and radiation. The Moon has no atmosphere. It's just lifeless rock. Mars has barely any atmosphere. A frozen desert. Earth is special, its air breathable, its surface habitable, its oceans vast. Looking at Earth from the Moon, as Apollo astronauts did, our world seems impossibly small. All human history occurred on that tiny sphere. Every war, every discovery, every love, every birth and death. Contained within that fragile blue dot. Carl Sagan captured this perspective in his Pale Blue Dot reflection, written after Voyager 1 photographed Earth from 4 billion miles away. Earth appeared as a single pixel, a tiny dot suspended in a sunbeam. Sagan wrote about our posturing, our imagined self-importance, our delusion that we have some privileged position in the universe. From cosmic distance, national borders vanish, political divisions become invisible. Conflicts seem absurd when viewed from space. The atmosphere doesn't recognize borders. Climate change affects everyone. Nuclear war would affect the entire planet. From space, we're clearly one world, one species, sharing one small home. This perspective shift is powerful. Astronauts often return changed, more concerned with Earth's fragility, more aware of humanity's interconnection. They've seen firsthand that we're all on this spaceship together, traveling through space at thousands of miles per second, utterly dependent on this thin shell of air and water. Earth is the only known world with life. Maybe life exists elsewhere. Probably it does. But we haven't found it yet. Every living thing we know inhabits this one planet. Every species, every ecosystem, every wilderness and city exists nowhere else. The universe contains perhaps 10 or 24 stars, maybe 10 to 24 planets. Earth is one. If it's destroyed or rendered uninhabitable, that's not a small local disaster. It's potentially the death of the only consciousness in vast regions of space, the silencing of the only voice that can speak for this corner of the cosmos. We face existential risks: nuclear war, climate change, asteroid impacts, pandemics, Artificial intelligence gone wrong. Some risks are self-inflicted, products of our technology outpacing our wisdom. Others are natural, threats the universe poses to any life anywhere. Yet we possess capabilities our ancestors couldn't imagine. We can deflect asteroids. We can detect pandemics and develop vaccines. We can monitor climate and potentially mitigate changes. We can build sustainable systems, regulate dangerous technologies, and cooperate globally. The overview effect inspires hope alongside concern. We're capable of solving problems if we choose. We've already done remarkable things: eradicated diseases, expanded knowledge, reduced poverty, extended lifespans. We've begun exploring space, planting footprints on the moon, sending robots to Mars. Looking at Earth from cosmic perspective, we see both fragility and potential. Fragility because one planet in an enormous universe harbors all known life. Potential because that life has produced technology, science, art, and consciousness that transform mere matter into meaning. Perhaps someday humans will inhabit other worlds. Mars could be terraformed, Venus cooled, moons settled. Perhaps we'll build space habitats, artificial worlds orbiting stars, expanding life beyond Earth. Perhaps we'll eventually spread throughout the galaxy, carrying Earth's biological heritage to countless star systems. This would be humanity's great project, making life multiplanetary, then interstellar, ensuring that no single catastrophe can extinguish consciousness in this region of space. We'd become guardians of life itself, preserving and propagating the universe's most complex creations. But that future requires surviving the present. We must navigate the dangerous transition from a single planet species to a spacefaring civilization. We must solve the problems we've created and manage the risks we face. The overview effect reminds us why this matters. Because Earth is precious, rare, and worth protecting. From space, Earth is beautiful beyond words. Blue oceans, white clouds, green and brown continents, glowing atmosphere. No artist could paint anything more lovely. No world we've discovered matches its beauty. Earth is a paradise compared to the lifeless rocks and gas giants surrounding us. We should treat it as such, protect its ecosystems, preserve its species, maintain its climate within habitable bounds. Not just for our benefit, though that's reason enough. But because Earth is special in the cosmos, a rare jewel where matter organized into life and consciousness, the cosmic perspective transforms how we see ourselves. We're not separate nations competing for resources. We're one species sharing one world, temporary custodians of something precious and rare. Our ancestors didn't see this. They lacked the overview effect, the ability to look back at Earth from space. We have no such excuse. We've seen our planet from beyond, understood our cosmic context, recognized our shared fate. The question is whether we'll act on this knowledge, whether the overview effect will transform not just individual astronauts, but all humanity. Understanding vast timescales. Human minds struggle with large numbers. 1 million seconds is about 11.5 days. 1 billion seconds is about 31.7 years. 1 trillion seconds is almost 32,000 years. These differences feel small when stated, just factors of 1,000, but represent enormous temporal spans. The universe is 13.8 billion years old. Earth formed 4.54 billion years ago. Life arose perhaps 3.8 billion years ago. Multicellular life evolved about 600 million years ago. Dinosaurs dominated from 230 to 66 million years ago. Homo sapiens emerged about 300,000 years ago. Recorded history spans maybe 5,000 years. Visualize this on a calendar year. If the Big Bang occurred on January 1st, our solar system formed in early September. Life appeared by late September. Multicellular life arose in mid-November. Dinosaurs went extinct on December 26th. Homo sapiens appeared at 11:40 p.m. on December 31st. Recorded history began in the last few seconds before midnight. All of human civilization. Agriculture, cities, writing, technology, everything we consider history. occurred in the final seconds of the cosmic year. We're newcomers, recent arrivals in an ancient universe. This perspective is humbling. The universe existed for over 9 billion years before Earth formed. Life existed on Earth for billions of years before humans. The cosmos doesn't center on us. We're latecomers to an ancient story. Yet we're also remarkable. In 300,000 years, we've gone from stone tools to spacecraft. We've developed language, writing, mathematics, science. We understand our cosmic context, measure the universe, probe its origins. No other species on Earth has done this. Perhaps no other species in the galaxy has done this. We're young but precocious. Looking forward, the timescales become even more overwhelming. The sun will shine for another 5 billion years. Stars will form for trillions of years. Black holes will persist for 10-100 years. The universe might exist forever, eternal expansion into infinite future. Compared to these timescales, human existence is infinitesimal. Even if humanity survives millions of years, becoming one of the longest-lived species, we'll occupy a tiny fraction of cosmic time. We're ephemeral patterns in an enduring cosmos. Geological time offers another scale. Mountains rise and erode over millions of years. Continents drift across the globe over hundreds of millions of years. Species evolve, dominate, go extinct. Individual species typically last a few million years. The entire fossil record we can observe spans about 600 million years, the period with readily preserved hard-bodied life. Life has survived multiple mass extinctions. 5 major extinction events punctuate the fossil record, each killing off large percentages of species. The Permian-Triassic extinction, 252 million years ago, killed an estimated 96% of marine species. The Cretaceous-Paleogene extinction 66 million years ago killed the dinosaurs. Yet life persisted. New species evolved to fill empty niches. Diversity rebounded over millions of years. Life is resilient across geological time, even if individual species and ecosystems are fragile. Humans exist in a brief window between vast past and vaster future. Behind us stretches billions of years of cosmic and biological evolution that made us possible. Ahead lies perhaps billions of years of future. If we survive, if we spread beyond Earth, if we become permanent rather than transient, our decisions matter on geological timescales. Climate change, biodiversity loss, nuclear waste. These affect not just our lifetimes, but thousands or millions of years ahead. Plastic pollution will persist for millennia. Radioactive waste remains dangerous for hundreds of thousands of years. Species extinction is permanent on human timescales, though evolution eventually produces new diversity. Understanding deep time changes priorities, short-term thinking, political cycles, quarterly profits, individual lifespans, becomes obviously inadequate. We need long-term thinking that considers centuries, millennia, even millions of years ahead. Indigenous cultures often consider 7 generations when making decisions, about 140 years. This is wise but still short by geological standards. We should think in terms of 10,000 years, 100,000 years, recognizing that our actions echo through deep time. The universe has been patient. It waited billions of years for stars to form, planets to coalesce, life to evolve, consciousness to arise. We're the product of this immense patience. Shouldn't we exercise similar patience, thinking in terms of civilizational timescales rather than human lifespans? Yet we must also act urgently. Species go extinct now. Climate changes now. Decisions made in coming decades will shape humanity's trajectory for millennia. We exist in a crucial moment when our choices determine whether humanity has a long future or brief one. Deep time grants perspective, but shouldn't paralyze action. Yes, we're tiny in the cosmic story. Yes, our individual lives are brief. But we're here now, in this moment, with power to influence what comes next. Our decisions ripple forward through time, affecting countless future generations. The universe gave us this moment. 13.8 billion years of cosmic evolution produced you, here, now, reading these words. You're the beneficiary of everything that came before. And you're the ancestor of everything that comes after, your choices shaping the trajectory of future centuries. Deep time is humbling and empowering simultaneously. Humbling because we're so recent, so brief. Empowering because we can think across these vast scales, can make decisions that honor deep time, can act as stewards for the billions of years ahead. Let's return to where we began. You, lying in darkness, breathing slowly, relaxing into the night. You are atoms. Hydrogen, oxygen, carbon, nitrogen, arranged in precise patterns. These atoms cycle through you constantly. The carbon in your body replaced itself multiple times during your life. You're not a fixed thing, but a dynamic process, a pattern that persists even as the materials change. Those atoms were forged in stars. Some were created in the Big Bang, the hydrogen, most of the helium. Others formed in stellar cores through fusion. Carbon, oxygen, nitrogen. Still others were scattered by dying stars. The iron, calcium, phosphorus in your bones and blood. The atoms in your left hand might come from different stars than those in your right. You're assembled from stellar debris scattered across the galaxy, gathered by gravity into the cloud that formed our solar system, incorporated into Earth, cycled through the biosphere, and temporarily organized into the pattern you call yourself. You're ancient and new simultaneously. The matter composing you is nearly as old as the universe. The pattern organizing that matter is unique to you, perhaps never existing before and never existing again in quite this form. You're connected to everything. The oxygen you breathe was exhaled by plants. The water you drink has cycled through clouds, rivers, oceans, other living things. The food you eat grew from nutrients that were once part of other organisms. You're not isolated. You're a node in vast networks of exchange, connecting all life on Earth. You're also connected to the cosmos. Cosmic rays from distant supernovae pass through your body constantly. Neutrinos from the sun stream through you, trillions per second, occasionally interacting with atoms. Gravitational waves from colliding black holes billions of light years away stretch and squeeze you infinitesimally as they pass. You're bathed in the cosmic microwave background, ancient photons from the universe's youth. You're rare, perhaps unique. We've found no other life anywhere. Maybe it exists. Probably it does. But we haven't confirmed it. For all we know with certainty, Earth is the only living world, and humans the only conscious beings in vast regions of space. You might be the cosmos's only way of knowing itself in trillions of cubic light years. Or you might be one among countless others, scattered through the galaxy, each gazing at the same stars, asking the same questions. Either way, your existence is remarkable. Either exceptionally rare or a common miracle repeated throughout the cosmos. You won't exist forever. The atoms composing you will continue, recycled into other forms. Your pattern will dissolve. The information encoding your memories, personality, thoughts will disperse into entropy. Someday, not even atoms will remain. Far in the future, even protons might decay. But for now, you exist. You're here, aware, thinking, feeling. You've traveled through time from the Big Bang to this moment, riding a wave of cosmic evolution that produced stars, planets, life, consciousness. You're the universe's autobiography, written in flesh and neurons. The cosmos is vast, ancient, mostly empty, yet it produced you. From quantum foam and curved space-time, from hydrogen and helium, from gravity and nuclear forces, from eons of stellar alchemy and biological evolution. You emerged. The universe made a pattern complex enough to understand itself, to ask why it exists, to experience wonder at its own grandeur. This moment, you reading these words, contemplating existence, is the universe becoming self-aware, not metaphorically, literally. You are the cosmos, locally organized, asking questions about its own nature. Rest in this knowledge. You're made of stars. You're related to everything alive. You're connected to the universe at its deepest levels. You're temporary, but part of something eternal. You're tiny, but contain multitudes. You're insignificant and precious simultaneously. The universe continues its journey through time. Stars burn, galaxies rotate, space expands, and within it all, briefly, you exist, aware, conscious, wondering, a temporary eddy in the cosmic flow, a pattern that arose, persisted for a moment, and will eventually fade. But not yet. For now, you breathe. Your heart beats. Neurons fire in your brain, generating thoughts, experiences, awareness. You are here, now, alive in the cosmos. Sleep now, cradled in the knowledge of your cosmic nature. The universe holds you, as it holds all things. The atoms in your body, forged in stellar cores, will never be destroyed, only transformed, reorganized, eventually returning to the cosmic cycle that produced them. You are the universe, dreaming itself into temporary awareness. Rest in that dream. The cosmos has been unfolding for 13.8 billion years. It will continue for billions or trillions more. Your brief moment of consciousness is your gift to the universe. Its chance to know itself, to appreciate its own beauty, to contemplate its own existence. Tomorrow you'll wake to sunlight. Photons that left the sun 8 minutes ago traveled across 93 million miles of space to illuminate your room and warm your skin. You'll breathe air enriched by plants. You'll eat food grown from soil. You'll move through a world shaped by billions of years of evolution and human history. But tonight, rest. Drift into sleep, knowing you're part of something vast and beautiful. The universe gave you this moment of awareness. However you choose to use it, whatever you do with your brief time as a conscious pattern in the cosmic flow, you're participating in the greatest story ever told. The universe's journey from simple hydrogen to complex life, from unconscious matter to self-aware mind. You are made of space, time, and reality itself. These aren't just topics to contemplate. They're what you are, at your most fundamental level. You are space-time curved slightly around mass. You are quantum fields vibrating in patterns complex enough to think. You are entropy temporarily organizing itself before returning to disorder. You are the cosmos, experiencing itself from one particular viewpoint for one brief span. And now, as consciousness fades into sleep, as your thoughts quiet and your awareness dims, remember, you're still here. The pattern continues. The atoms remain. The process of being you persists, even as conscious awareness recedes. Sleep well, temporary pattern in the eternal cosmos. Sleep well, briefly organized stardust. Sleep well, conscious mind arising from unconscious matter. Sleep well, small voice in the universal silence. Sleep well, brief moment of awareness in eternity. The universe dreams through you. Let your dreams return to the universe. Let consciousness rest, knowing it will wake again to another day, another chance to witness the cosmic story unfolding. The stars shine whether you watch or not. The galaxies rotate whether you observe or not. Space expands whether you measure or not. But when you watch, observe, and measure, the universe gains something it otherwise lacks. A witness, an appreciator, a consciousness that says, "I see you, cosmos, and you are beautiful." Tomorrow you'll say it again. But tonight, simply rest, float in the darkness. Feel the earth beneath you, spinning through space. Sense the air around you, the atmosphere that makes life possible. Breathe the breath that connects you to all living things. You are home. Not just in your bed, in your room, in your house, but home in the cosmos, in the universe that created you, in the space and time that hold you. This is your place. You belong here, a natural part of reality, as much as stars belong in space, as much as waves belong to oceans. Rest now. The universe has waited billions of years to produce this moment of awareness. It can wait while you sleep. Tomorrow brings another opportunity to contemplate, to wonder, to understand. But tonight, Simply be. Be the pattern that you are. Be the briefly conscious arrangement of ancient atoms. Be the local organization fighting entropy for a moment before returning to simplicity. Be the question the universe asks itself. Be the answer you provide by existing. Close your eyes. Feel the darkness. Let your mind quiet. The cosmos holds you, as it holds all things, in the eternal embrace of space and time and reality itself. You are made of stars, time-traveling matter, conscious dust. You are beautiful. You are precious. You are temporary. You are eternal. You are insignificant. You are everything. Quantum whispers. In the silence of your room, in the darkness behind your closed eyes, something extraordinary is happening. At scales too small to see, too subtle to sense, reality is breathing. Your body, this temporary vessel of consciousness, is not solid. It never was. Between the atoms that compose you lies emptiness, vast spaces where nothing material exists. If you could remove all this empty space, compress every atom in every human who ever lived into pure matter with no gaps, the entire species would fit inside a single sugar cube. You are mostly absence, mostly potential, mostly space itself, held together by invisible forces, animated by fields you cannot perceive. At this moment, in the space between your atoms, virtual particles are flickering into existence. Electron-positron pairs materialize from nothing, exist for an infinitesimal instant, then annihilate, returning their borrowed energy to the vacuum. This happens constantly, everywhere, always. The emptiness inside you seethes with quantum activity, a froth of possibility that never rests. These are not metaphors for something else. This is what you are, at your most fundamental level. You are quantum foam given temporary form, probability waves collapsed into apparent solidity, fields vibrating in patterns complex enough to dream. The universe contains perhaps 10 or 24 stars, maybe 10 to 24 planets. Earth is one. If it's destroyed or rendered uninhabitable, that's not a small local disaster. It's potentially the death of the only consciousness in vast regions of space, the silencing of the only voice that can speak for this corner of the cosmos. We face existential risks: nuclear war, climate change, asteroid impacts, pandemics, artificial intelligence gone wrong. Some risks are self-inflicted, products of our technology outpacing our wisdom. Others are natural, threats the universe poses to any life anywhere. Yet we possess capabilities our ancestors couldn't imagine. We can deflect asteroids. We can detect pandemics and develop vaccines. We can monitor climate and potentially mitigate changes. We can build sustainable systems, regulate dangerous technologies, and cooperate globally. The overview effect inspires hope alongside concern. We're capable of solving problems if we choose. We've already done remarkable things: eradicated diseases, expanded knowledge, reduced poverty, extended lifespans. We've begun exploring space, planting footprints on the moon, sending robots to Mars. Looking at Earth from cosmic perspective, we see both fragility and potential. Fragility because one planet in an enormous universe harbors all known life. Potential because that life has produced technology, science, art, and consciousness that transform mere matter into meaning. Perhaps someday humans will inhabit other worlds. Mars could be terraformed, Venus cooled, moons settled. Perhaps we'll build space habitats, artificial worlds orbiting stars, expanding life beyond Earth. Perhaps we'll eventually spread throughout the galaxy, carrying Earth's biological heritage to countless star systems. This would be humanity's great project, making life multiplanetary, then interstellar, ensuring that no single catastrophe can extinguish consciousness in this region of space. We'd become guardians of life itself, preserving and propagating the universe's most complex creations. But that future requires surviving the present. We must navigate the dangerous transition from a single planet species to a spacefaring civilization. We must solve the problems we've created and manage the risks we face. The overview effect reminds us why this matters. Because Earth is precious, rare, and worth protecting. From space, Earth is beautiful beyond words. Blue oceans, white clouds, green and brown continents, glowing atmosphere. No artist could paint anything more lovely. No world we've discovered matches its beauty. Earth is a paradise compared to the lifeless rocks and gas giants surrounding us. We should treat it as such, protect its ecosystems, preserve its species, maintain its climate within habitable bounds. Not just for our benefit, though that's reason enough. But because Earth is special in the cosmos, a rare jewel where matter organized into life and consciousness, the cosmic perspective transforms how we see ourselves. We're not separate nations competing for resources. We're one species sharing one world, temporary custodians of something precious and rare. Our ancestors didn't see this. They lacked the overview effect, the ability to look back at Earth from space. We have no such excuse. We've seen our planet from beyond, understood our cosmic context, recognized our shared fate. The question is whether we'll act on this knowledge, whether the overview effect will transform not just individual astronauts, but all humanity. Understanding vast timescales. Human minds struggle with large numbers. 1 million seconds is about 11.5 days. 1 billion seconds is about 31.7 years. 1 trillion seconds is almost 32,000 years. These differences feel small when stated, just factors of 1,000, but represent enormous temporal spans. The universe is 13.8 billion years old. Earth formed 4.54 billion years ago. Life arose perhaps 3.8 billion years ago. Multicellular life evolved about 600 million years ago. Dinosaurs dominated from 230 to 66 million years ago. Homo sapiens emerged about 300,000 years ago. Recorded history spans maybe 5,000 years. Visualize this on a calendar year. If the Big Bang occurred on January 1st, our solar system formed in early September. Life appeared by late September. Multicellular life arose in mid-November. Dinosaurs went extinct on December 26th. Homo sapiens appeared at 11:40 p.m. on December 31st. Recorded history began in the last few seconds before midnight. All of human civilization. Agriculture, cities, writing, technology, everything we consider history, occurred in the final seconds of the cosmic year. We're newcomers, recent arrivals in an ancient universe. This perspective is humbling. The universe existed for over 9 billion years before Earth formed. Life existed on Earth for billions of years before humans. The cosmos doesn't center on us. We're latecomers to an ancient story. Yet we're also remarkable. In 300,000 years, we've gone from stone tools to spacecraft. We've developed language, writing, mathematics, science. We understand our cosmic context, measure the universe, probe its origins. No other species on Earth has done this. Perhaps no other species in the galaxy has done this. We're young but precocious. Looking forward, the timescales become even more overwhelming. The sun will shine for another 5 billion years. Stars will form for trillions of years. Black holes will persist for 10-100 years. The universe might exist forever, eternal expansion into infinite future. Compared to these timescales, human existence is infinitesimal. Even if humanity survives millions of years, becoming one of the longest-lived species, we'll occupy a tiny fraction of cosmic time. We're ephemeral patterns in an enduring cosmos. Geological time offers another scale. Mountains rise and erode over millions of years. Continents drift across the globe over hundreds of millions of years. Species evolve, dominate, go extinct. Individual species typically last a few million years. The entire fossil record we can observe spans about 600 million years, the period with readily preserved hard-bodied life. Life has survived multiple mass extinctions. 5 major extinction events punctuate the fossil record, each killing off large percentages of species. The Permian-Triassic extinction, 252 million years ago, killed an estimated 96% of marine species. The Cretaceous-Paleogene extinction 66 million years ago killed the dinosaurs. Yet life persisted. New species evolved to fill empty niches. Diversity rebounded over millions of years. Life is resilient across geological time, even if individual species and ecosystems are fragile. Humans exist in a brief window between vast past and vaster future. Behind us stretches billions of years of cosmic and biological evolution that made us possible. Ahead lies perhaps billions of years of future. If we survive, if we spread beyond Earth, if we become permanent rather than transient, our decisions matter on geological timescales. Climate change, biodiversity loss, nuclear waste. These affect not just our lifetimes, but thousands or millions of years ahead. Plastic pollution will persist for millennia. Radioactive waste remains dangerous for hundreds of thousands of years. Species extinction is permanent on human timescales, though evolution eventually produces new diversity. Understanding deep time changes priorities, short-term thinking, political cycles, quarterly profits, individual lifespans, becomes obviously inadequate. We need long-term thinking that considers centuries, millennia, even millions of years ahead. Indigenous cultures often consider 7 generations when making decisions, about 140 years. This is wise but still short by geological standards. We should think in terms of 10,000 years, 100,000 years, recognizing that our actions echo through deep time. The universe has been patient. It waited billions of years for stars to form, planets to coalesce, life to evolve, consciousness to arise. We're the product of this immense patience. Shouldn't we exercise similar patience, thinking in terms of civilizational timescales rather than human lifespans? Yet we must also act urgently. Species go extinct now. Climate changes now. Decisions made in coming decades will shape humanity's trajectory for millennia. We exist in a crucial moment when our choices determine whether humanity has a long future or brief one. Deep time grants perspective, but shouldn't paralyze action. Yes, we're tiny in the cosmic story. Yes, our individual lives are brief. But we're here now, in this moment, with power to influence what comes next. Our decisions ripple forward through time, affecting countless future generations. The universe gave us this moment. 13.8 billion years of cosmic evolution produced you, here, now, reading these words. You're the beneficiary of everything that came before. And you're the ancestor of everything that comes after, your choices shaping the trajectory of future centuries. Deep time is humbling and empowering simultaneously. Humbling because we're so recent, so brief. Empowering because we can think across these vast scales, can make decisions that honor deep time, can act as stewards for the billions of years ahead. Let's return to where we began. You, lying in darkness, breathing slowly, relaxing into the night. You are atoms. Hydrogen, oxygen, carbon, nitrogen, arranged in precise patterns. These atoms cycle through you constantly. The carbon in your body replaced itself multiple times during your life. You're not a fixed thing, but a dynamic process, a pattern that persists even as the materials change. Those atoms were forged in stars. Some were created in the Big Bang, the hydrogen, most of the helium. Others formed in stellar cores through fusion. Carbon, oxygen, nitrogen. Still others were scattered by dying stars. The iron, calcium, phosphorus in your bones and blood. The atoms in your left hand might come from different stars than those in your right. You're assembled from stellar debris scattered across the galaxy, gathered by gravity into the cloud that formed our solar system, incorporated into Earth, cycled through the biosphere, and temporarily organized into the pattern you call yourself. You're ancient and new simultaneously. The matter composing you is nearly as old as the universe. The pattern organizing that matter is unique to you, perhaps never existing before and never existing again in quite this form. You're connected to everything. The oxygen you breathe was exhaled by plants. The water you drink has cycled through clouds, rivers, oceans, other living things. The food you eat grew from nutrients that were once part of other organisms. You're not isolated. You're a node in vast networks of exchange, connecting all life on Earth. You're also connected to the cosmos. Cosmic rays from distant supernovae pass through your body constantly. Neutrinos from the sun stream through you, trillions per second, occasionally interacting with atoms. Gravitational waves from colliding black holes billions of light years away stretch and squeeze you infinitesimally as they pass. You're bathed in the cosmic microwave background, ancient photons from the universe's youth. You're rare, perhaps unique. We've found no other life anywhere. Maybe it exists. Probably it does, but we haven't confirmed it. For all we know with certainty, Earth is the only living world, and humans the only conscious beings in vast regions of space. You might be the cosmos's only way of knowing itself in trillions of cubic light years. Or you might be one among countless others, scattered through the galaxy, each gazing at the same stars, asking the same questions. Either way, your existence is remarkable. Either exceptionally rare or a common miracle repeated throughout the cosmos. You won't exist forever. The atoms composing you will continue, recycled into other forms. Your pattern will dissolve. The information encoding your memories, personality, thoughts will disperse into entropy. Someday, not even atoms will remain. Far in the future, even protons might decay. But for now, you exist. You're here, aware, thinking, feeling. You've traveled through time from the Big Bang to this moment, riding a wave of cosmic evolution that produced stars, planets, life, consciousness. You're the universe's autobiography, written in flesh and neurons. The cosmos is vast, ancient, mostly empty, yet it produced you. From quantum foam and curved space-time, from hydrogen and helium, from gravity and nuclear forces, from eons of stellar alchemy and biological evolution. You emerged. The universe made a pattern complex enough to understand itself, to ask why it exists, to experience wonder at its own grandeur. This moment, you reading these words, contemplating existence, is the universe becoming self-aware, not metaphorically, literally. You are the cosmos, locally organized, asking questions about its own nature. Rest in this knowledge. You're made of stars. You're related to everything alive. You're connected to the universe at its deepest levels. You're temporary, but part of something eternal. You're tiny, but contain multitudes. You're insignificant and precious simultaneously. The universe continues its journey through time. Stars burn, galaxies rotate, space expands, and within it all, briefly, you exist, aware, conscious, wondering, a temporary eddy in the cosmic flow, a pattern that arose, persisted for a moment, and will eventually fade. But not yet. For now, you breathe. Your heart beats. Neurons fire in your brain, generating thoughts, experiences, awareness. You are here, now, alive in the cosmos. Sleep now, cradled in the knowledge of your cosmic nature. The universe holds you, as it holds all things. The atoms in your body, forged in stellar cores, will never be destroyed, only transformed, reorganized, eventually returning to the cosmic cycle that produced them. You are the universe, dreaming itself into temporary awareness. Rest in that dream. The cosmos has been unfolding for 13.8 billion years. It will continue for billions or trillions more. Your brief moment of consciousness is your gift to the universe. Its chance to know itself, to appreciate its own beauty, to contemplate its own existence. Tomorrow you'll wake to sunlight. Photons that left the sun 8 minutes ago traveled across 93 million miles of space to illuminate your room and warm your skin. You'll breathe air enriched by plants. You'll eat food grown from soil. You'll move through a world shaped by billions of years of evolution and human history. But tonight, rest. Drift into sleep, knowing you're part of something vast and beautiful. The universe gave you this moment of awareness. However you choose to use it, whatever you do with your brief time as a conscious pattern in the cosmic flow, you're participating in the greatest story ever told. The universe's journey from simple hydrogen to complex life, from unconscious matter to self-aware mind. You are made of space, time, and reality itself. These aren't just topics to contemplate. They're what you are, at your most fundamental level. You are space-time curved slightly around mass. You are quantum fields vibrating in patterns complex enough to think. You are entropy temporarily organizing itself before returning to disorder. You are the cosmos, experiencing itself from one particular viewpoint for one brief span. And now, as consciousness fades into sleep, as your thoughts quiet and your awareness dims, remember, you're still here. The pattern continues. The atoms remain. The process of being you persists, even as conscious awareness recedes. Sleep well, temporary pattern in the eternal cosmos. Sleep well, briefly organized stardust. Sleep well, conscious mind arising from unconscious matter. Sleep well, small voice in the universal silence. Sleep well, brief moment of awareness in eternity. The universe dreams through you. Let your dreams return to the universe. Let consciousness rest, knowing it will wake again to another day, another chance to witness the cosmic story unfolding. The stars shine whether you watch or not. The galaxies rotate whether you observe or not. Space expands whether you measure or not. But when you watch, observe, and measure, the universe gains something it otherwise lacks. A witness, an appreciator, a consciousness that says, "I see you, cosmos, and you are beautiful." Tomorrow you'll say it again. But tonight, simply rest, float in the darkness, feel the earth beneath you, spinning through space. Sense the air around you, the atmosphere that makes life possible. Breathe the breath that connects you to all living things. You are home. Not just in your bed, in your room, in your house, but home in the cosmos, in the universe that created you, in the space and time that hold you. This is your place. You belong here, a natural part of reality, as much as stars belong in space, as much as waves belong to oceans. Rest now. The universe has waited billions of years to produce this moment of awareness. It can wait while you sleep. Tomorrow brings another opportunity to contemplate, to wonder, to understand. But tonight, simply be. Be the pattern that you are. Be the briefly conscious arrangement of ancient atoms. Be the local organization fighting entropy for a moment before returning to simplicity. Be the question the universe asks itself. Be the answer you provide by existing. Close your eyes. Feel the darkness. Let your mind quiet. The cosmos holds you, as it holds all things, in the eternal embrace of space and time and reality itself. You are made of stars, time-traveling matter, conscious dust. You are beautiful. You are precious. You are temporary. You are eternal. You are insignificant. You are everything. Quantum whispers. In the silence of your room, in the darkness behind your closed eyes, something extraordinary is happening. At scales too small to see, too subtle to sense, reality is breathing. Your body, this temporary vessel of consciousness, is not solid. It never was. Between the atoms that compose you lies emptiness, vast spaces where nothing material exists. If you could remove all this empty space, compress every atom in every human who ever lived into pure matter with no gaps, the entire species would fit inside a single sugar cube. You are mostly absence, mostly potential, mostly space itself, held together by invisible forces, animated by fields you cannot perceive. At this moment, in the space between your atoms, virtual particles are flickering into existence. Electron-positron pairs materialize from nothing, exist for an infinitesimal instant, then annihilate, returning their borrowed energy to the vacuum. This happens constantly, everywhere, always. The emptiness inside you seethes with quantum activity, a froth of possibility that never rests. These are not metaphors for something else. This is what you are, at your most fundamental level. You are quantum foam given temporary form, probability waves collapsed into apparent solidity, fields vibrating in patterns complex enough to dream. Why? Because these patterns are mathematically optimal for certain growth processes. A sunflower arranging seeds according to Fibonacci spirals packs seeds most efficiently. A nautilus adding chambers in golden ratio proportions maintains the same shape as it grows. Nature discovers mathematics not through calculation, but through evolution, selecting patterns that work. Hexagons tile perfectly, leaving no gaps. That's why honeycombs use hexagonal cells. Bees evolved to build the most efficient structure for storing honey with minimum wax. That's why basalt columns form hexagons as lava cools and contracts. That's why some planetary atmospheres develop hexagonal storm patterns at their poles. Fluid dynamics finding the most stable configuration. Fractals repeat patterns at different scales. Zoom into a fractal, and you find the same shapes repeating smaller and smaller. Coastlines are fractal. Their irregular shape looks similar, whether you zoom in on meters or kilometers. Mountains are fractal. Their rough, jagged profile repeats at multiple scales. Clouds, river networks, lightning bolts, blood vessels. All fractal, patterns within patterns, self-similar across scales. Fractals optimize surface area relative to volume. Your lungs are fractal, branching repeatedly, creating enormous surface area for gas exchange within limited space. Blood vessels fractally branch to supply nutrients to every cell efficiently. The universe's large-scale structure, the cosmic web, has fractal properties, matter clumping at multiple scales in similar patterns. The Mandelbrot set, perhaps the most famous fractal, emerges from a simple mathematical equation applied repeatedly. Its boundary, infinitely complex, contains limitless detail. Zoom forever, and you'll always find new patterns, new structures, new complexity. This infinite detail emerges from an equation simple enough to write on a postcard. Reality appears to work similarly. Simple rules, applied repeatedly, generate vast complexity. Physics has only a few fundamental forces and particles, yet from these simple ingredients emerges everything. Galaxies, ecosystems, consciousness. Symmetry governs everything. Physical laws remain the same if you rotate your reference frame. That's rotational symmetry, and it leads to conservation of angular momentum. Laws remain the same if you shift in time. That's temporal symmetry, leading to conservation of energy. Laws remain the same if you move through space. Spatial symmetry, leading to conservation of momentum. Every conservation law in physics corresponds to a symmetry. This profound connection, Noether's theorem, shows that the universe's patterns aren't arbitrary. They reflect deep mathematical structure, symmetries that constrain what's possible, rules that shape reality's architecture. Crystals grow in specific geometries determined by how atoms pack together. Salt forms cubes. Snowflakes form six-pointed stars. Quartz grows hexagonal crystals. These shapes aren't designed. They emerge inevitably from atomic structure, from how molecules minimize energy while arranging themselves. Your body follows geometric patterns laid down billions of years ago. Bilateral symmetry, left and right sides mirroring each other, appears in most animals, likely because swimming or crawling in a specific direction benefits from symmetric propulsion. Radial symmetry, arranging body parts around a central axis, appears in jellyfish and starfish, creatures that don't move directionally. The golden ratio appears in your face. The distance from your chin to your nose compared to nose to eyebrows approximately follows phi. So does the ratio of your hand segments. These proportions feel aesthetically pleasing because they're written into our biology, into how growth processes generate form. Pentagons and five-fold symmetry rarely appear in crystals. You can't tile a plane with regular pentagons, but appear frequently in life. Five-petaled flowers are common. Starfish have 5 arms. Your hand has 5 fingers. Life exploits symmetries that crystalline matter cannot. using the flexibility of carbon chemistry to explore geometric possibilities unavailable to simple crystals. Sacred geometry. The ancient study of these patterns wasn't mystical nonsense but intuitive mathematics. Ancient peoples noticed that the same shapes appeared throughout nature. They recognized circles in the sun and moon, spirals in shells, fractals in lightning. They used these patterns in architecture, art, and ritual, aligning human creation with natural order. The Platonic solids: tetrahedron, cube, octahedron, dodecahedron, icosahedron, are the only 5 perfectly regular 3-dimensional polyhedra possible. Ancient Greeks saw deep significance in these forms. Modern science finds them everywhere. Viral capsids often take icosahedral forms. Crystals embody cubic or octahedral symmetry. Molecules arrange themselves according to these geometric constraints. Mathematics isn't invented but discovered. We don't create patterns, we find them, already present in reality's structure. The circle existed before humans named it. Fractals existed before Mandelbrot visualized them. The golden ratio operated in Nautilus shells millions of years before anyone calculated its value. You are built from geometry. DNA's double helix is a geometrical shape. 2 spirals intertwined, turning in precise angles, measured in nanometers, following rules of chemistry that are ultimately rules of quantum mechanics and electromagnetic force. The shape encodes information, but the information requires the shape. Your cells divide according to geometric principles. 1 becomes 2, 2 become 4, 4 become 8. Exponential growth following simple geometric rules. The developing embryo folds in specific patterns, sheets of cells curving, tubes forming, 3-dimensional structure emerging from 2-dimensional layers through geometric transformations. Atoms arrange in spherical probability clouds around nuclei, geometry emerging from quantum mechanics. Molecules bond at specific angles. Water at 104.5 degrees, methane at 109.5 degrees. Angles determined by how electron clouds distribute themselves in space, by electromagnetic forces seeking lowest energy configurations. The universe is mathematical, not because mathematics describes it, but because mathematics is it. Space has geometry. It curves according to Einstein's equations. Time has geometric properties. It can be treated as a dimension, woven with space into space-time. Even quantum fields have geometric aspects. Gauge theories describe forces as geometries of abstract spaces. Perhaps the deepest insight of modern physics is that reality, at its foundations, is geometric, not made of substance, but of shape, pattern, structure, symmetry. Matter and energy are manifestations of geometric properties of fields. Particles are vibrations, waves, excitations in geometric substrates. You perceive geometry directly. Your visual system detects edges, lines, curves before processing objects. Your sense of balance depends on geometric sensing organs in your inner ear. Semicircular canals, detecting rotation in 3 perpendicular planes. Your brain represents space geometrically. Place cells firing when you occupy specific locations. Grid cells creating coordinate systems. Boundary cells encoding spatial edges. You navigate using mental maps, geometric representations of space. You recognize faces by proportions, relationships between features, geometric patterns. You appreciate beauty partly through symmetry, golden ratios, harmonic proportions. Geometric properties your brain processes automatically. Geometry connects you to cosmos. The same patterns in your fingerprint appear in spiral galaxies. The same fractals in your lungs appear in the cosmic web. The same symmetries in your face appear in flowers, snowflakes, starfish. You are not separate from nature's geometry, but part of it, another expression of the same underlying patterns. Sacred geometry is the recognition that certain patterns are universal, fundamental, repeated at all scales from quantum to cosmic. These aren't human projections onto neutral reality, but structures inherent in existence itself. Rest now in geometric space. Your body lying horizontal, perpendicular to gravity's vertical pull. your closed eyes creating darkness, a zero-dimensional point of awareness in three-dimensional space. Your breath moving in and out, oscillating like a wave, like a pendulum, following the mathematics of harmonic motion. You are pattern made of patterns, resting in space that has pattern, breathing according to patterns, thinking thoughts that follow neural patterns, patterns all the way down, patterns all the way up, patterns intersecting and interfering, creating the temporary stability you call self. The universe is geometry in motion. You are a geometric pattern that learned to contemplate geometry, shape studying shape, form aware of form, pattern recognizing pattern, sleep geometric being. Let your conscious awareness dissolve back into simpler patterns. Let the complex symmetries of waking thought relax into the simpler geometries of rest. Let the intricate tessellation of your daily life simplify into the clean lines of sleep. The patterns that make you will persist through the night, stable enough to reconstitute tomorrow, flexible enough to allow rest now. You are geometry, temporarily self-aware, briefly organized, forever part of the mathematical structure that is reality itself. The cosmic ocean. Imagine space not as emptiness but as ocean, not liquid water, but something more fundamental, a medium through which everything moves, in which everything exists. You are not in space. You are of space, made from it, a temporary configuration of its properties. Like a wave is not separate from ocean, but a pattern in it. You are not separate from space-time, but a pattern within it. Every movement you make is movement through space-time, not just space. When you walk across a room, you travel through space, but also inevitably through time. The two are woven together, inseparable. You cannot move through space without moving through time. You cannot exist in space without existing in time. Einstein revealed that space and time form a unified four-dimensional manifold. Space-time. Events don't happen in space at a time. They happen in space-time, at specific coordinates specifying where and when simultaneously. Your life is not a three-dimensional body moving through time. It's a four-dimensional structure, a world line extending from birth to death through space-time. Picture this. If you could see 4 dimensions simultaneously, you would see your entire life at once. Every moment from conception to death laid out as a continuous structure. The baby you are still exists in the past regions of space-time. The elder you will become already exists in future regions. All of you across all times forms a single, unified four-dimensional object. This isn't metaphysical speculation. This is the geometry revealed by relativity. The universe is a four-dimensional space-time fabric, and you are an extended structure within it, perceiving only three-dimensional slices moment by moment as your consciousness moves along your world line. Space-time isn't passive container, but active participant. Mass curves it, energy shapes it. Gravity is not a force pulling through space, but the curvature of space-time itself. Planets orbit, not because the sun pulls them, but because they follow the curved geometry the sun creates in space-time. Imagine space-time as a trampoline. Place a heavy ball, the sun, in the center, and it creates a depression. Smaller balls, planets, placed nearby, will roll around the depression, following the curved surface. This is gravity, not attraction, but geometry, not force, but shape. But unlike a trampoline curved in 3 dimensions, space-time curves in 4 dimensions, 3 spatial plus 1 temporal, time curves as well as space. Near massive objects, time runs slower. At the event horizon of a black hole, time stops entirely from an external perspective. You curve space-time around you. Your mass, small as it is, creates a tiny gravitational field, a minute curvature in the fabric. This curvature extends infinitely in all directions, growing weaker with distance, but never reaching zero. Your gravitational influence touches the entire universe, however faintly. Every atom curves space-time. Every photon curves it. Everything that exists warps the fabric around itself, creating geometry, influencing how everything else moves. The universe is a tapestry of intersecting curvatures, each object shaping space around itself, each curve influencing every other curve. Space-time has texture, structure, dynamics. It can ripple, gravitational waves. It can expand, cosmic expansion. It might connect to itself in strange topologies. Wormholes. It might tear. Black hole singularities where curvature becomes infinite, where geometry breaks down. Space-time might be quantized at the smallest scales. Planck length, about 10 around 35 meters. Below this scale, our concepts of distance might lose meaning. Space might be granular, discontinuous, made of discrete units like pixels forming a screen. Time might come in minimum increments, each chronon the smallest possible duration. Or space-time might be emergent, not fundamental, but arising from something deeper. Quantum entanglement might weave space-time into existence, connections between particles creating the illusion of distance, the geometry emerging from information patterns. This is speculative, but hints at how strange reality's foundations might be. You swim through space-time. Every motion navigates this four-dimensional ocean. When you move quickly through space, you move more slowly through time. Time dilation. Astronauts in fast orbits age slightly slower than people on Earth. GPS satellites must account for both their orbital speed, slowing time, and weaker gravity, speeding time, to maintain accuracy. If you could travel near light speed, time would slow dramatically from external perspectives. You could travel years through space while experiencing only days of subjective time. You'd move through space quickly by moving through time slowly. The two dimensions trading off, maintaining a constant speed through space-time itself. Light travels through space at light speed, but through time, not at all. Photons experience no time between emission and absorption. From light's perspective, the entire journey happens instantly. Light travels at the maximum speed through space by not traveling through time at all. You travel mostly through time, barely through space. Sitting still, you move through time at maximum rate. 1 second per second from your perspective. When you walk, run, drive, fly, you trade tiny amounts of time motion for space motion, slowing your temporal velocity infinitesimally to move spatially. The cosmic speed limit isn't just about space, it's about space-time. All objects move through space-time at the same total speed, light speed, but this speed can be divided between spatial and temporal dimensions. Massive particles move mostly through time. Massless particles move entirely through space. Space-time breathes with dark energy's expansion. Every second, space itself grows, creating more distance between galaxies. This expansion doesn't happen in space. Space itself expands, carrying contents with it, like dots on a balloon's surface, separating as the balloon inflates. The expansion is accelerating. Dark energy, whatever it is, pushes space apart faster and faster. Eventually, distant galaxies will recede beyond the cosmic horizon, moving away faster than light can close the distance, disappearing from our observable universe forever. Space-time has a horizon, the cosmological event horizon beyond which we can never see, never reach, never communicate with. Events occurring beyond this horizon are causally disconnected from us, existing in regions of space-time we cannot influence, and that cannot influence us. But within our horizon, we're connected. Photons from distant galaxies reach us, carrying information across space-time. Gravitational waves from merging black holes stretch and compress space-time as they pass. Subtle ripples in the fabric, carrying news of ancient cataclysms. You exist within space-time's horizon, able to receive information from a sphere centered on you, extending billions of light years in every direction. This is your observable universe, your accessible space-time, the region with which you can interact. Space-time will outlast you. Long after your world line ends, space-time continues, carrying other patterns, other structures, other brief moments of consciousness wondering at existence. The fabric persists while individual waves rise and fall, appear and disappear, form and dissolve. Yet you affect space-time permanently. Your world line is part of space-time's history forever. The gravitational waves you create, infinitesimal as they are, propagate outward eternally, never disappearing entirely, carrying information about your existence through space-time infinitely. Every action leaves permanent marks in space-time's geometry. Nothing is truly erased. Information is preserved in the fabric structure, in correlations between quantum states, in patterns too subtle to observe, but theoretically recoverable. You are not traveling through space-time. You are part of space-time's structure, a feature of its geometry, a configuration of its quantum fields. When you perceive yourself moving through space and time, you're actually experiencing your consciousness tracing along your world line, experiencing sequential slices of a structure that exists all at once in 4 dimensions. This moment, you reading these words, is a specific point in space-time, coordinates specifying where and when you are. This point is eternal, unchanging, permanent. It always was and always will be this moment, this place, this configuration of matter and consciousness. Yet from within, you experience flow, change, temporal passage. Past recedes into memory. Future approaches as unknown. Present feels fleeting, always slipping into past before you can grasp it fully. Both perspectives are true. Space-time is fixed, eternal, block universe where all moments exist simultaneously. Yet consciousness flows through it, experiencing one slice at a time, perceiving duration, witnessing change, living the illusion, or perhaps the reality, of temporal passage. This paradox cannot be fully resolved. Physics describes the block universe, the eternal 4-dimensional structure. Consciousness experiences flow, becoming, the arrow of time. Perhaps both descriptions capture different aspects of reality. Perhaps there are truths about existence that cannot be unified into single, consistent narratives. Rest now in space-time's embrace. The fabric holds you, has always held you, will always hold you. Your world line is woven into its structure permanently, indelibly, eternally. You are swimming through the cosmic ocean, though the ocean is not separate from you. You are wave and water simultaneously, pattern and medium, form and fabric. You are space-time knowing itself, geometry experiencing its own curvature, the universe exploring what it's like to be this particular configuration of its own structure. The ocean has no surface, no shore, no boundary. It extends infinitely in every direction. Space expanding forever, time flowing eternally forward, and perhaps backward in ways we don't understand. Dimensions curving and connecting in configurations beyond visualization. You float in this infinite ocean, not drowning but breathing, not sinking but suspended, held up by geometry itself, by the fact that space-time has structure, that it curves around mass, that it creates the illusion, or reality, of gravity holding you to Earth. Feel the ocean around you, not with physical senses. Space-time has no temperature, no viscosity, no texture you can touch. Feel it with understanding, with the knowledge that you exist within this medium, that every photon reaching your eyes travel through it, that every sound you hear is vibrations in matter suspended in it, that every thought you think occurs in a brain structured by it. The cosmic ocean is not elsewhere. It is here, now, everywhere, always. You have never been outside it, never been separate from it, never been anything other than a temporary pattern within its vastness. And yet, what a pattern you are. Complex beyond measure, organized beyond comprehension, conscious in ways that space-time itself is not, or perhaps is, through you. You are the ocean's way of knowing itself, of experiencing its own existence, of asking what it means to be. Sleep now, swimmer in space-time. Let your consciousness drift through the 4th dimension, experiencing the temporal flow that carries you from moment to moment, from now toward future, from wake toward sleep, from question toward rest. The ocean will carry you through the night as it carries everything, as it has always carried everything. You are safe in its embrace, held by geometry, supported by curvature, floating in the fundamental fabric of existence itself. Tomorrow, you will wake to continue swimming, continue experiencing your journey along your world line, continue being this particular wave in the cosmic ocean. But tonight, let yourself dissolve slightly. Let the boundaries soften. Let the distinction between swimmer and ocean blur. You are space-time, temporarily configured to experience itself. Rest in this knowledge. Rest in this truth. Rest in the cosmic ocean that is your true home, your only home, your eternal home. The fabric embraces you. The geometry cradles you. The fourth dimension carries you gently forward through time, second by second, breath by breath, heartbeat by heartbeat, toward the morning that already exists in future space-time, waiting for your world line to intersect it. Swim gently, cosmic being. Float peacefully, four-dimensional structure. Rest deeply, temporary pattern in the eternal ocean of space-time. The philosophy of impermanence. Everything changes, nothing lasts, all things pass away. This is not pessimism but physics, not philosophy but thermodynamics, not opinion but observation. The stars will die. Every last one will exhaust its fuel, collapse, explode, or fade into darkness. The longest-lived stars might shine for tens of trillions of years, but eventually, their nuclear furnaces will cool, their light will dim, their warmth will cease. Galaxies will disperse. Over incomprehensible timespans, stars will be ejected from their galaxies, scattered into intergalactic space. The beautiful spiral structures we observe today will unwind, dissipate, dissolve into individual stars, wandering separately through cosmic void. Black holes will evaporate. Through Hawking radiation, even these seemingly eternal objects will slowly lose mass, growing hotter as they shrink, eventually vanishing in final bursts of energy after 100 years or more. Nothing survives forever, not even the universe's most enduring structures. Atoms will decay, protons might be stable, or they might slowly transform into lighter particles with half-lives exceeding 1034 years. Given enough time, all complex matter might dissolve into radiation and fundamental particles, the structures that took billions of years to build unraveling into simplicity. The universe itself will end. Whether in heat death, big rip, big crunch, or vacuum decay, the cosmos as we know it will cease. All structure, all complexity, all organization will eventually give way to maximum entropy, to equilibrium, to the final state from which nothing further can emerge. This is the ultimate impermanence. Not just individual things passing, but everything passing. Not just temporary structures dissolving, but all structures dissolving. Not just local order becoming chaos, but universal order becoming chaos. Yet impermanence is not tragedy. It is condition of existence itself. Things exist precisely because they are temporary, because they emerge and dissolve, because they participate in the flow of becoming, rather than the stasis of eternal being. Consider a wave on the ocean. It rises, travels across the water's surface, then falls and disappears. Was the wave ever separate from the ocean? No. It was always water, always part of the ocean, temporarily configured into a traveling pattern before rejoining the vast body from which it never truly separated. The wave's impermanence doesn't diminish its reality. While it existed, it was genuinely a wave, with height, length, speed, direction. It carried energy and momentum. It could erode shores, rock boats, be observed and measured. Its temporary nature didn't make it less real. You are like this wave. You arise from the universe, exist for a time, then return to the universe. Your impermanence doesn't diminish your reality. While you exist, you genuinely exist, with thoughts, feelings, experiences, agency. You affect the world, carry energy and information, can be observed and measured. Your temporary nature doesn't make you less real, less valuable, less significant. It makes you what you are. A process, not an object. A pattern, not a substance. A dynamic flow, not a static thing. The Buddhist concept of anicca, impermanence, recognizes this truth. Nothing has permanent self-nature. Everything depends on causes and conditions. Everything arises when conditions support it and ceases when conditions change. Nothing stands alone, independent, eternal. This applies to everything. Your body replaces most atoms every few years. Your cells continuously die and are replaced. Your thoughts arise and pass away, each thought lasting mere seconds before dissolving into the next. Your emotions flow through you like weather, constantly changing, never fixed. Even your sense of self is impermanent. The you of childhood is gone, replaced by the you of adolescence, then adulthood, then middle age, then elderhood. Each stage is genuinely you, yet each is different. Which is the real you? All of them, and none of them. You are not a fixed entity, but a process of continuous becoming. Memories change each time you recall them, neural patterns rewriting themselves, making memory reconstruction rather than retrieval. Your personality shifts gradually over decades, shaped by experiences, relationships, choices. The self is not unchanging essence, but dynamic pattern, constantly reforming, never identical from moment to moment. Heraclitus understood, no man steps in the same river twice, for it's not the same river and he's not the same man. Both river and man are flows, processes, continuous becomings. The names remain the same while the reality continuously changes. Impermanence enables change. If everything were permanent, no growth would be possible, no learning, no evolution, no adaptation. The universe would be static, frozen, dead. Impermanence allows novelty, creativity, possibility. It allows you to become different from what you were, to grow beyond your current limitations, to change in response to experience. Impermanence also means loss. Everything you love will eventually be lost. Every relationship ends through distance, change, or death. Every experience fades into memory, and memories themselves fade with time. Every achievement becomes history, relegated to the past, replaced by new achievements or forgotten entirely. This loss is painful. The human heart grieves impermanence, wishes things could last forever, clings to what is passing even as it slips away. We build monuments to resist impermanence, write books to preserve knowledge, create art to transcend our mortality. We yearn for the permanent in a universe that offers only the temporary. Yet acceptance of impermanence brings peace. When you stop demanding that things last forever, you can appreciate them fully now. When you recognize that this moment is fleeting, you can be present in it rather than constantly anticipating future or dwelling in past. When you understand that loss is inevitable, you can love without the anxiety of preservation, engage without the burden of permanence. Japanese aesthetics embrace impermanence in the concept of mono no aware, the pathos of things, the bittersweet awareness that beauty is enhanced by its transience. Cherry blossoms are lovely precisely because they bloom briefly. Autumn leaves captivate because they soon fall. A sunset is magnificent because it lasts only minutes. If cherry blossoms bloomed forever, would we marvel at them? If autumn lasted eternally, would we gather to watch leaves turn? If sunset never ended, would we pause to admire it? Beauty gains power from impermanence, preciousness from scarcity, poignancy from inevitable loss. Your life is beautiful, partly because it is finite. Each day matters because you have only so many. Each relationship is precious because it won't last forever. Each experience is valuable because you cannot repeat it identically. Mortality gives life urgency, significance, weight. In cosmological perspective, impermanence is absolute. The universe may last trillions of years, but even that is finite compared to eternity. Every structure, every pattern, every organization, no matter how grand, will eventually dissolve. Stars, galaxies, black holes, even space-time itself might be temporary, fleeting configurations in something larger, stranger, more fundamental. Yet consciousness exists now. Love exists now. Beauty exists now. These are not diminished by their impermanence, but defined by it. They mean something precisely because they are rare, brief, contingent. They are precious because they are temporary. Consider a candle burning in darkness. The flame consumes the wax, transforming solid matter into light and heat and gaseous products. The candle cannot burn forever. Eventually, the wax depletes and the flame dies. Yet while it burns, it illuminates. While it exists, it serves its purpose. Its temporary nature doesn't negate its value. You are this flame. You burn with metabolic fire, consuming food, transforming it into energy and experience and action. You cannot burn forever. Eventually, your fuel depletes, your flame dies. Yet while you burn, you illuminate. While you exist, you serve purposes known and unknown. Your temporary nature doesn't negate your value. Buddhism teaches that suffering arises from attachment, from grasping at the impermanent as if it were permanent, from demanding that the temporary endure eternally. Let go of this demand, and suffering diminishes. Accept impermanence, and peace becomes possible. This doesn't mean not caring, not loving, not engaging. It means loving without grasping, engaging without clinging, caring while knowing that all things pass. It means being fully present because you recognize that presence is all there is. The past is gone, the future unformed. Only this moment exists, and this moment too is passing. Even as you read these words, the moment shifts, the present becomes past, new moments arrive. You cannot hold on to now any more than you can hold on to water. The tighter you grasp, the faster it flows away. So open your hands, release your grip. Let the impermanent be impermanent. Let things arise and pass away according to their nature. Don't demand that reality conform to your preferences. Accept what is as it is, knowing that it will soon be different. This acceptance is not resignation, but wisdom. Not giving up, but letting go. Not passivity, but alignment with reality's nature. You cannot stop impermanence any more than you can stop time itself. But you can flow with it, dance with it, participate in it consciously rather than resisting it futilely. Everything ends. This conversation ends. This night ends. This life ends. This universe ends. Nothing gold can stay. Not because reality is cruel, but because permanence is impossible. Because existence itself is flow, process, continuous transformation. But while things last, however briefly, they are real, valuable, meaningful. Your life matters even though it's finite. Your love is genuine even though it's temporary. Your experiences are significant even though they're fleeting. The universe is beautiful even though it's impermanent. Perhaps especially because it's impermanent. Rest now in this knowledge. You are temporary, and that's okay. You are impermanent, and that's appropriate. You will end, and that's natural. Not tragic, not wrong, not a problem to be solved. Just the way things are, the condition of existence, the price of being something rather than nothing. Sleep, temporary pattern. Sleep, fleeting configuration. Sleep, brief moment of consciousness in eternal flow. Tomorrow you will arise, changed slightly from today, continuing your journey through impermanence, participating in the great dance of becoming and unbecoming that is reality itself. But tonight, rest. Let go of permanence. Release the need for things to last. Accept the flowing nature of all that exists. Be at peace with impermanence, with change, with loss, with the ultimate ending that comes for all things. For now, you exist. And that is enough. That is everything. That is the miracle, the mystery, the gift. You exist briefly in a universe that mostly doesn't. You are conscious, temporarily, in a cosmos that is mostly unconscious. You are complex, impermanently, in a reality that tends towards simplicity. This makes you rare. This makes you precious. This makes you significant, not despite your impermanence, but because of it. Sleep now, golden thing that cannot stay. Sleep peacefully, knowing that your temporary nature doesn't diminish your worth. Sleep deeply, accepting that all things pass, including you, including this moment, including everything. The universe holds you for this brief time. Be grateful for the holding, for the time, for the brief gift of existence. And rest. Epilogue. In the end, there is only this moment, not tomorrow, which hasn't arrived, not yesterday, which no longer exists. Only now, this breath, this heartbeat, this awareness, reading these final words. All the cosmic grandeur we've explored, the billions of galaxies, the depths of space-time, the quantum foundations, the billions of years past and future, all of it exists only here, now, in your present awareness. The past is memory traces in your neurons. The future is neural patterns projecting possibilities. Both exist only now, as current brain states, as present moments of consciousness, experiencing what was, and imagining what might be. You cannot touch yesterday. You cannot grasp tomorrow. You can only be here, in the eternal present, where all experience actually occurs. This moment contains everything. The entire universe, as you know it, exists in your present awareness. The stars shine now in your mind's eye. Time flows now through your consciousness. Reality manifests now in your experience. And this now never ends. Tomorrow, when it arrives, will also be now. Yesterday, when it occurred, was also now. There has never been a moment that wasn't now, and there never will be. Now is eternal, continuous, the only time that ever truly exists. You are always here. You are always now. You can never be anywhere else, anyone else. This is your home, your only home, the present moment, the eternal now. The universe gave you this gift. Consciousness, awareness, the ability to experience now from a particular perspective. For a brief span, you are the universe's way of being present to itself, of experiencing now from inside, of witnessing reality from within. What a strange and beautiful gift. What an improbable arrangement of atoms and energy. What a brief, precious window of awareness. And now, as this journey through space and time and reality comes to rest, as words fade into silence and thoughts dissolve into sleep, remember, you are stardust, dreaming. You are the universe, knowing itself. You are time, experiencing now. You are space, folded into awareness. You are matter, organized into consciousness. You are energy, flowing through patterns. You are everything and nothing, significant and insignificant, temporary and eternal. You are exactly what you need to be, where you need to be, when you need to be. Here, now, breathing, aware, existing. Let that be enough. Let that be everything. Let that be peace. Sleep now, child of stars and time. Sleep deeply, pattern in the cosmic weave. Sleep peacefully, brief moment of awareness in the eternal now. The universe dreams through you, and now you dream with the universe. Good night, consciousness. Good night, cosmos. Good night.